Imagine looking up at the sun on an ordinary afternoon, that familiar golden disk that's been rising faithfully every morning for 4.5 billion years, and instead of seeing steady, reliable light, you witness something impossible. A flash, a brightening beyond comprehension, the sky turning white, then blue-white, as our star suddenly releases more energy in a single moment than it has produced in its entire lifetime. It's the kind of thought that seems almost absurd, isn't it? Our gentle sun, that reliable furnace that warms our days and paints our sunsets, exploding? Tonight, we're going to explore that impossible thought together. We're going to imagine what would happen if our sun, that medium-sized, middle-aged star that has been so faithfully stable for billions of years, suddenly went supernova, if it exploded with the violence of a massive dying star, releasing more energy in a few seconds than it normally produces in its entire 10 billion year lifetime. Hello, and welcome to the Sleepy Astronomer. If this is your first time drifting through the cosmos with me, welcome. I'm so glad you're here. And if you've travelled with me before through the quiet corners of space, it's wonderful to have you back for what might be our most explosive journey yet. Whether you're settling into bed, curled up in a favourite spot, or perhaps lying somewhere under that very sun we're about to imagine losing in the most dramatic way possible, I'm so grateful you're here to explore this question with me. If you enjoy these peaceful explorations of the cosmos, I'd be so grateful if you'd subscribe to join us for more cosmic journeys. And if this question intrigues you, a gentle like helps others discover these late-night wanderings through space. Now, before we go any further, let me offer you this profound comfort. Our sun cannot explode. Not as a supernova. It's physically impossible. Our sun simply doesn't have enough mass. You'd need a star at least 8 to 10 times more massive than our sun for it to go supernova. And our sun is, well, it's perfectly average, wonderfully, safely average. What we're about to explore is pure imagination, a thought experiment that helps us understand both the incredible violence of stellar explosions and the remarkable stability of our own star. It's safe here. We're imagining together, and when we're done, the sun will still be exactly where it's always been, faithfully fusing hydrogen into helium in its core, keeping us warm and alive, and with absolutely no plans to explode for the simple reason that it can't. But here's what makes this question so fascinating. It's not just about disaster or fear, it's about appreciation. When you imagine your sun exploding, even knowing it's impossible, you begin to understand just how fortunate we are to have the star we do. When you walk through the physics of what a supernova actually is, you start to see the incredible violence that forges the elements we're made of, and you realize that somewhere, out there in the universe, stars are exploding right now, creating the building blocks of future planets, future life, future civilizations. And perhaps most remarkably, you realize that you exist because ancient stars did explode. Every atom in your body, heavier than hydrogen and helium, the calcium in your bones, the iron in your blood, the oxygen you're breathing right now, was forged in the heart of an exploding star billions of years ago. You are quite literally made of stardust, made of the remnants of ancient cosmic violence. Tonight, we'll explore what a supernova actually is and why our sun is safely exempt from such a fate. We'll walk through what would happen if, impossibly, our sun did explode. We'll follow the light, the radiation, the blast wave. We'll see what would be destroyed and what might be created. We'll visit real supernovae that we've observed, stars that have died in spectacular fashion, their light travelling across the galaxy to reach our telescopes. And perhaps most importantly, we'll learn to appreciate the remarkable stability of our gentle sun, the fact that it rises every morning, burns steadily all day, and will continue to do so for another 5 billion years. The gift of a star that's just the right size to live a long, peaceful life rather than burning bright and dying young. So settle in, take a deep breath, and let yourself relax into this journey. The question is dramatic. What if the sun exploded? The answer. Well, the answer involves some of the most powerful and beautiful physics in the entire universe. Let's start with the most comforting fact in this entire exploration. Our sun is safe. Wonderfully, reliably, almost boringly safe. It cannot go supernova, no matter how dramatic that would be, no matter how interesting it might make our cosmic neighborhood. The universe has rules. And one of those rules is that only massive stars get to have explosive endings. Our sun simply doesn't qualify. Think of it this way. Stars, like people, have destinies largely determined by their, let's call it their starting weight. A star's mass at birth determines almost everything about its life. How hot it burns, how long it lives, and most importantly for our purposes tonight, how it dies. And our sun is what you might call a middleweight, not small enough to burn forever as a dim red dwarf, but definitely not massive enough for the kind of spectacular exit we're imagining. To go supernova, a star needs to be at least 8 to 10 times more massive than our sun. Some estimates put it even higher. That's not just a little bit bigger. That's an entirely different category of star. It's the difference between a campfire and a blast furnace. Both involve fire, sure, but the scale is utterly different. Our sun, bless it, is a G-type main sequence star. Scientists call it a yellow dwarf, though that name is a bit misleading, because it's neither particularly yellow nor particularly small. It's actually more of a white colour when you see it from space. And it's bigger than about 80% of all stars in our galaxy. But compared to the true giants, the massive stars that do go supernova, our sun is positively modest. The sun has been burning steadily for 4.5 billion years now, and it has another 5 billion years or so to go. That's a good, long, stable life. It's the kind of star you'd want if you were, say, trying to evolve complex life on a nearby planet, which is convenient because that's exactly what happened. We're here because our sun is the kind of star that doesn't do anything dramatic or unexpected. It just shows up to work every day, does its job and goes home, the reliable co-worker of stars. When our sun does eventually die, in about 5 billion years, and please note that this gives us plenty of time to make other arrangements. It won't explode. Instead, it will swell into a red giant, probably engulfing Mercury and Venus, and possibly Earth in the process. That sounds dramatic, but it's actually quite gradual. This expansion happens over millions of years. You could watch it your entire life and barely notice the difference. It's the opposite of sudden. After the red giant phase, the sun will shed its outer layers in a gentle puff. Scientists call this a planetary nebula, which is a confusing name because it has nothing to do with planets, but astronomy is full of historical naming choices that don't quite make sense anymore. And what's left will collapse into a white dwarf, a dense, hot ember about the size of Earth, slowly cooling over trillions of years. It's a peaceful death, as deaths go quiet, dignified, the kind of ending you'd want after a long, productive life. But the massive stars, oh, they have a very different story. These are the stars that live fast and die young, stars with 8, 10, 20, even 100 times the mass of our sun. They burn through their fuel at a furious rate, converting hydrogen to helium to carbon to oxygen and onwards, up the periodic table at a pace that would make our sun look positively lazy. Where our sun will spend 10 billion years on the main sequence, contentedly fusing hydrogen, these massive stars might last only a few million years. In cosmic terms, they're born, live and die in the blink of an eye. And here's where the physics gets truly fascinating. Let me walk you through what happens inside one of these massive stars as it approaches the end of its life, because understanding this helps us appreciate what we're imagining when we think about our sun exploding. A star is essentially a balancing act. Gravity wants to crush everything inward toward the center. Nuclear fusion in the core creates heat and pressure that push outward. For most of a star's life, these two forces are in equilibrium. The star is stable, burning steadily, holding its shape against its own gravity through the sheer power of the nuclear furnace at its heart. Our sun fuses hydrogen into helium, and it's been doing this for billions of years. When it eventually runs low on hydrogen in its core, it will start fusing helium into heavier elements, but it won't get much further than that. It just doesn't have the mass, the gravity, the sheer crushing pressure to continue up the periodic table. But a massive star has enough gravity to keep going. After hydrogen, it fuses helium into carbon, then carbon into oxygen, oxygen into neon, neon into magnesium, silicon into, and here's where things get interesting, iron. Iron is special. Iron is the end of the line. Here's why. Fusion releases energy because it creates elements with a more stable nuclear configuration. When you fuse lighter elements, you get energy out. That's what powers stars. But iron? Iron is the most stable element. Fusing iron into heavier elements doesn't release energy. It requires energy. It's an energy sink, not an energy source. So when a massive star starts creating iron in its core, it's essentially building its own coffin. The iron core grows, layer by layer, element by element, until it reaches a critical mass, and then gravity wins. The core collapses, not gradually, not slowly. In about 1 second, an iron core roughly the size of Earth collapses into a ball about 10 miles across. The outer layers of the star, suddenly unsupported, fall inward at a significant fraction of the speed of light. And then they hit the collapsed core and rebound. Imagine dropping a rubber ball. When it hits the ground, it bounces back up. Now imagine that on a stellar scale, with layers of the star that collectively weigh more than our entire sun, slamming into an impossibly dense core and rebounding outward at speeds up to 10% the speed of light. That rebound, that shockwave racing outward through the star, is what we call a supernova, and the energy releases, it's hard to comprehend. A supernova, in just a few seconds, releases more energy than the star emitted during its entire lifetime, more energy than our sun will produce in 10 billion years of steady burning. It's so bright that a single exploding star can briefly outshine an entire galaxy containing hundreds of billions of normal stars. And here's the beautiful part, the part that makes supernovae more than just cosmic catastrophes. This violence creates, in the incredible heat and pressure of the explosion, elements heavier than iron are forged: gold, platinum, uranium, all the heavy elements that can't be made inside even the most massive stars, because iron was the end of the line for fusion. These elements are created in the explosion itself. Every gold ring, every platinum catalyst in a car, every trace of iodine in your thyroid, every atom of molybdenum in your enzymes, all of it was made in a supernova. The violence that can destroy planets light years away is the same violence that creates the elements necessary for rocky planets and complex life. You cannot have one without the other. The universe requires both creation and destruction, and supernova are where that duality is most perfectly expressed. Our sun will never do this. It will never forge iron. It will never collapse and rebound. It will never scatter elements across light years of space. It will live its long, quiet life and die its peaceful death. And we should be profoundly grateful for that, because we need that stability. Life needs that stability. Civilization needs that stability. But somewhere in our galaxy right now, a massive star is approaching the end of its life, building iron in its core, preparing, though it has no consciousness to know it, for a spectacular end. And when it explodes, whenever that is, tonight, tomorrow, 1,000 years from now, its light will eventually reach us. We'll see it as a new star in the sky, a bright point where no star was visible before. And we'll watch from the safety of our orbit around our gentle, stable, wonderfully average sun, and perhaps we'll appreciate it just a little bit more, knowing what could have been, but isn't. Knowing that we live in the care of a star that will never surprise us with violence, only with its reliable, steady, life-giving light. So when we imagine our sun exploding in this thought experiment, we're really asking, what would it be like if our sun were a completely different kind of star? If we orbited something massive and short-lived instead of something moderate and long-lived? If we lived under the light of a star with a dramatic ending written into its future, instead of the peaceful fade we can actually expect? It's a question worth exploring, because the answer teaches us both about the incredible physics of stellar death and about the remarkable gift of having the sun we do. So now we arrive at the heart of our impossible scenario. We've established that our sun can't explode, but for the sake of understanding, for the sake of appreciating both the violence that exists in the universe and the gentleness we're blessed with, let's imagine it anyway. Let's imagine that somehow, impossibly, our sun had the mass and the iron core and the gravitational pressure necessary to go supernova. What would that actually look like? What would happen? And perhaps most importantly for those of us who enjoy these late-night explorations of physics, what would we experience? Let's set up our scenario carefully. We're not going to have the sun gradually evolve into a massive star over millions of years. That would rather defeat the purpose and also take far too long. Instead, let's imagine a cosmic swap. At noon on an ordinary Tuesday, our sun is instantly replaced by a massive star. At the very end of its life, a star that has already built up that iron core we talked about, that's already at the critical moment when gravity is about to win. This star is about 15 times more massive than our sun. It's been burning for perhaps 10 million years, a lifetime that seems long to us but is remarkably brief for a star. And it's reached the end. The iron core in its centre has grown to about 1.5 times the mass of our entire sun, compressed into a sphere roughly the size of Earth, and it's about to collapse. Now here's where we need to talk about speed, because the timescales involved in a supernova are remarkable. That iron core, it collapses in less than a second. In about the time it takes you to snap your fingers, an object the size of Earth crushes down to a ball about 10 miles across. The inner core becomes so dense that protons and electrons are forced together to form neutrons, the very definition of a neutron star, creating something so incomprehensibly dense that a teaspoon of it would weigh about as much as Mount Everest. That's quite a lot to happen in less than a second. The universe can be surprisingly fast when it decides to be dramatic. The collapse releases an absolutely staggering amount of gravitational potential energy. When something falls, it converts potential energy into kinetic energy. This is why dropping something from higher up means it hits the ground harder. Now imagine something with the mass of our entire sun falling inward on itself from the size of Earth down to the size of a city. The energy released is beyond anything we experience in daily life. Most of that energy, about 99% of it, gets carried away by neutrinos. These are strange little particles that barely interact with matter. They're so aloof, so antisocial, that they can pass through entire planets without noticing. Right now, billions of neutrinos from the Sun are passing through your body every second, and you don't feel a thing. They're the introverts of the particle world. In a supernova, the neutrino burst is so intense that even though these particles barely interact with anything, even though they're famous for their ability to pass through matter as if it wasn't there, they carry away enough energy to blow the star apart. Think about that for a moment. Particles that normally ignore matter entirely are so numerous, so energetic, that they become the mechanism of destruction. The neutrinos race outward at essentially the speed of light. In our scenario, they would reach Earth in about 8 minutes and 20 seconds, the same time it normally takes light from the Sun to reach us. Even in this intense burst, most would still pass harmlessly through Earth. But we have neutrino detectors, deep underground laboratories designed to catch these elusive particles, and they would absolutely notice they'd detect a surge unlike anything they'd ever seen before. This would be our first warning. 8 minutes and 20 seconds after the star exploded, neutrino detectors around the world would go absolutely haywire. Scientists monitoring them would have perhaps a few seconds to think, "That's odd," before the light arrived. Because right after the neutrinos, racing along behind them like a wave following the ripple, comes the light. The shockwave from the core collapse races outward through the star's outer layers at velocities approaching 10% the speed of light. That's about 67 million miles per hour. It's the kind of speed where relativistic effects start to matter, where the physics starts to get weird and wonderful. And this explosion releases light. So much light. A supernova, at its peak, can output as much light as an entire galaxy. Think about that. A galaxy contains hundreds of billions of stars, each one pouring out energy, and a single supernova can briefly match their collective brightness. If our Sun did this, the light would reach Earth about 8 minutes after the explosion, and what we'd see would be, well, it's hard to adequately describe, but let's try. Imagine you're outside on that Tuesday afternoon. It's a normal day. The Sun is where it always is, that familiar bright disk in the sky, and then, over the course of a few seconds, not instantly, but quickly, it gets brighter, much brighter, alarmingly brighter. Within moments, the Sun would be bright enough that you couldn't look at it even briefly without damaging your eyes. Which is already true of the normal Sun, to be fair, but this would be far more intense. It would be like staring at a welding arc. The kind of brightness where your first instinct is to look away, and your second instinct is to wonder why the sky is turning strange colours. Because here's what would happen to the sky. It would get bright, very bright. That comfortable blue would wash out to a pale, almost white colour. Then, as the intensity increased, it might take on an almost blue-white quality, like the colour of the hottest part of a flame. The Sun wouldn't look like a disk anymore. It would be a point source of light so intense that it hurt to have it anywhere in your field of view. This would be daylight brighter than any daylight Earth has ever seen, brighter than the desert at noon, brighter than snowfields under a summer sun, bright enough that the word daylight seems inadequate, bright enough to be visible through closed eyelids, bright enough to cast shadows sharper than any shadows you've ever seen. And this brightness would continue, not for seconds, but for days, for weeks. A supernova doesn't flash and disappear. It builds to peak brightness over about a week, maintains that peak for another week or two, and then gradually fades over months. So we're not talking about a momentary flash, we're talking about a sustained, overwhelming brightness that would be the new normal for quite some time. Well, it would be the new normal if there was anyone left to experience it, which brings us to the less pleasant aspects of what's happening. Because it's not just visible light that's flooding toward Earth, it's the entire electromagnetic spectrum. Gamma rays, X-rays, ultraviolet radiation, intense enough to give you a sunburn in seconds. All of this is racing toward us along with the visible light. The gamma rays and X-rays would arrive first, slamming into Earth's atmosphere. Here's where we'd see our first protective effect. The atmosphere would absorb them. The ozone layer would be utterly overwhelmed, destroyed by the intensity of high-energy photons. But in being destroyed, it would protect the surface. At least initially, the atmosphere itself would act as a shield. But that absorption has consequences. When gamma rays and X-rays are absorbed by the atmosphere, that energy has to go somewhere. It goes into heating the atmosphere. The upper atmosphere would heat up dramatically, expanding outward. Some of it would be heated enough to escape Earth's gravity entirely. We'd be losing atmosphere with every moment that passed. The UV radiation, normally kept in check by our ozone layer, would now reach the surface with full intensity, and UV radiation is damaging to biological molecules. DNA absorbs UV radiation, and when it does, it can cause mutations, breaks in the double helix, errors that cells can't always repair. On the side of Earth facing the Sun, any life exposed to this radiation would face immediate danger. Plants would begin to die, their chlorophyll molecules damaged by the intense UV. Animals, including any humans who happen to be outside, would suffer severe radiation damage. This would be acute radiation syndrome developing in minutes. The infrared radiation, the heat, would also be intense. We're talking about a heat source more than 1,000,000 times brighter than the normal sun temperatures on the day side, would spike within minutes. Not everywhere would reach the same temperature. The tropics would heat more than the poles, clear areas more than cloudy ones. But everywhere would get dramatically hotter. Water would begin to evaporate rapidly. Lakes, rivers, even the surface of the ocean would start to boil. Not all at once. The ocean contains a tremendous amount of thermal mass. But the surface would heat, steam would rise, and the water cycle would go into overdrive. Clouds would form rapidly from all that evaporation, providing some protection, some shielding from the intense light, but not enough. The electromagnetic pulse would wreak havoc with electronics. Satellites would be the first to go, their delicate electronics fried by the intense radiation. Communications would fail. GPS would stop working. The International Space Station, if it happened to be on the day side of Earth, would be in severe trouble. On Earth's surface, power grids would destabilize. The sudden heating of the atmosphere would create massive electrical disturbances. Transformers would overload. Power would become unreliable at precisely the moment when people would most desperately need it. And here's something interesting about this scenario. Earth's night side would be temporarily protected. Half the planet, the half facing away from this catastrophe, would be shielded by the mass of Earth itself. They'd experience the electromagnetic pulse, certainly, and they'd see their communications fail, their satellites go dark. But they wouldn't experience the direct radiation, the intense heat, the light bright enough to damage eyes. For a few hours, the night side would have a reprieve. People there would know something was terribly wrong. All their technology would be failing. They'd see the sky lit up in strange ways from scattered light in the atmosphere, but they wouldn't yet be in immediate danger. Of course, Earth rotates, and in about 12 hours that protected night side would rotate to face the exploded sun. There would be no sunrise. There would be a merging into a brilliance that would make the word sunrise seem quaint and inadequate. But let's pause here and remember something important. This is all happening in our imagination. This is a thought experiment. Right now, as you listen to this, the sun is doing exactly what it's always done. It's fusing hydrogen into helium in its core at a steady, reliable rate. It's producing exactly the amount of light and heat it produced yesterday, and tomorrow it will produce the same amount again. The sun outside your window, or the sun that will be outside your window when day comes, that sun is safe, stable, gentle. Everything we're describing is impossible for it to do. But understanding what would happen if it could helps us appreciate the physics of what actually does happen in the universe. Somewhere in our galaxy, perhaps right now, a star is exploding, experiencing everything we're describing. And if there are planets around that star, if there was life on those planets, this is what they're experiencing. A supernova, despite being called an explosion, isn't really like any explosion we experience in daily life. The core collapse takes less than a second, but the light show builds over days and persists for weeks or months. It's an explosion in the same way that the sunrise is sudden. Technically, yes, but the word doesn't quite capture the experience. This happens because the shockwave takes time to traverse the massive outer envelope of the star. As it does, it heats this material to incredible temperatures. The expanding cloud of stellar material becomes luminous, and this luminosity persists because the explosion has created radioactive isotopes, primarily nickel-56, that decay and release energy, keeping the expanding debris hot and glowing for months. So, in our scenario, after that initial spike in brightness, there would be a sustained period, weeks long, where the supernova remnant continued to dominate the sky. It would gradually fade, yes, but slowly. Each day it might be slightly dimmer than the day before, but each day it would still be far brighter than the normal sun ever was. We're safe. Our sun is safe. And that safety is a gift we should never take for granted. There's something beautifully strange about those first 8 minutes. 8 minutes and 20 seconds to be precise. That's how long it takes light to travel from the sun to Earth, and in our scenario, that's how long we have between when the star explodes and when we find out about it. It's a grace period of the most peculiar kind. The star has exploded. The neutrinos are already racing toward us at nearly the speed of light. The electromagnetic radiation, all that deadly light and heat and radiation we talked about, is following right behind them. But for those 8 minutes, Earth exists in a state of blissful ignorance. The sun in our sky looks perfectly normal, because the light we're seeing was emitted before the explosion happened. Think about what's happening during these minutes. It's an ordinary Tuesday, remember. We set this at noon, so somewhere on Earth people are having lunch. Someone in Sao Paulo is eating a sandwich in a park, feeling the warmth on their face. Someone in Mumbai is finishing their afternoon tea. A student in Chicago is sitting in a classroom, staring out the window, watching dust motes dance in a shaft of sunlight. And all of them are seeing a lie. Not intentionally, of course. The universe doesn't lie. It just takes its time sharing information. They're seeing the sun as it was 8 minutes ago, when it was still stable, still fusing hydrogen into helium, still being the reliable star we've always known. The photons hitting their skin, the light entering their eyes, all of it came from a star that no longer exists. They're warming themselves by the memory of a sun. There's something almost philosophical about this, isn't there? We're always seeing the past when we look at anything. Even the person sitting across from you, you're seeing them as they were a few nanoseconds ago. the time it took light to bounce off them and reach your eyes. When you look at the moon, you're seeing it as it was 1.3 seconds ago. When you look at the stars, you're seeing ancient history. Some of those stars might not even exist anymore, but we won't know for years, centuries, millennia. But usually those time delays don't matter. The person across from you hasn't changed much in a few nanoseconds. The moon is pretty much the same as it was 1.3 seconds ago. But our sun has changed rather significantly. It's exploded. It's gone from being a stable, friendly star to being a rapidly expanding cloud of stellar debris, radiating more energy than 1 billion normal suns. That's a fairly major status update, and Earth just hasn't received the notification yet. Let's follow what's happening during these 8 minutes, both at the Sun and here on Earth. At the Sun, or rather, where the Sun used to be, the explosion is well underway. That collapsed core, that neutron star or possibly even a black hole that formed in less than a second, is now surrounded by layers of stellar material, racing outward at tremendous speeds. The inner layers are moving fastest, having gotten the full force of that rebound off the collapsed core. The outer layers are still accelerating, still being pushed by the pressure of all that energy. The expanding debris cloud is glowing with incredible brightness. It's hot, millions of degrees. At those temperatures, everything is ionized. Electrons strip from atoms, creating what's called a plasma. It's the fourth state of matter after solid, liquid, and gas, and it's what most of the visible universe is made of. Stars are plasma, lightning is plasma, and now the remains of our sun are plasma, expanding outward in all directions. The light from this plasma is streaming out into space. Visible light, yes, but also ultraviolet, X-rays, gamma rays, the whole electromagnetic spectrum, and all of it is racing outward at light speed, heading toward Earth and every other planet in the solar system, carrying news of the catastrophe. Meanwhile, on Earth, everything seems fine. Better than fine, really. It's a beautiful day in São Paulo. The weather in Mumbai is pleasant. Chicago is enjoying typical autumn sunshine. Solar panels across the world are generating electricity at their normal rates. Plants are photosynthesizing. Gardeners are watering their tomatoes. People are making plans for dinner, for next week, for next year. The International Space Station is passing over the Pacific Ocean. The astronauts inside might be looking out the window, watching Earth rotate below them, perhaps marveling at how peaceful everything looks from up here. The sun, from their perspective, looks exactly like it always does. A bright disk, too intense to look at directly, providing the light that makes Earth's oceans shimmer and its clouds glow white. They have no idea that in a few minutes, that view is going to change dramatically. Down on Earth, scientists at neutrino detectors are going about their normal work. These detectors, places like Super Kamiokande in Japan or IceCube at the South Pole, spend their time catching the occasional neutrino from the sun, or from cosmic rays, or from other distant sources. It's painstaking work. Neutrinos are notoriously difficult to detect because they barely interact with matter. You need enormous detectors and a lot of patience. But in a few minutes, their patience is going to be rewarded in a way they probably never expected. Actually, rewarded might not be the right word. Overwhelmed might be more accurate. Let's think about what people are doing in these last few minutes of normalcy. Someone, somewhere, is being born. The very last human to be born under light from the original sun, though of course neither they nor their parents will ever know this distinction. Someone else is getting married, making promises about a future that's about to become vastly more complicated. Someone is buying a house, signing a 30-year mortgage that will outlive the sun's explosion by several decades, though they'll face rather different problems than property taxes. A farmer in Iowa is checking their crops, satisfied with how the corn is growing. A fisher in Norway is bringing in their catch. A teacher in Kenya is explaining photosynthesis to a classroom of students, telling them how plants use sunlight to make food, not knowing that this process is about to become a historical curiosity rather than an ongoing reality. And somewhere, inevitably, someone is looking up at the sun. Maybe they're an amateur astronomer, checking to see if there are any sunspots visible. Maybe they're just someone who likes looking at the sky. They're using proper eye protection, of course. You should never look directly at the sun, but they're observing it, watching it, seeing it appear completely normal. That person is looking at the last normal light from the sun that will ever reach Earth. They're witnessing the end of an era without knowing it. They might even be feeling a moment of peace, of connection with the cosmos, thinking about how that star has been shining steadily for billions of years and will continue to do so for billions more. They would be wrong about that last part, but you can't really blame them. The universe hasn't told them otherwise yet. At 8 minutes, we're getting close. The neutrinos have almost reached Earth. They left the exploding star 8 minutes ago, and they've been travelling at essentially light speed ever since, crossing that vast gulf of space between the Sun and Earth behind them. By mere seconds comes the light. At 8 minutes and 15 seconds, the neutrinos hit Earth's atmosphere. Most pass straight through. That's what neutrinos do. They zip through the entire planet as if it weren't there, but some, a tiny fraction, interact with the detectors. And because there are so many neutrinos in this burst, about 10 billion times more than the Sun normally produces, even a tiny fraction is more than enough. The neutrino detectors go wild, every sensor lighting up simultaneously. The computers recording data at rates they were never designed to handle, scientists staring at their screens in disbelief, checking if there's been some kind of equipment malfunction, because nothing natural should produce a signal like this. Nothing natural they've ever seen anyway. They have about 5 seconds to figure out what's happening before the light arrives. 5 seconds. That's not much time. Not enough to alert anyone, not enough to prepare. Barely enough to think, what on earth? Before realizing that whatever is happening, it's not on Earth. It's at the Sun. At 8 minutes and 20 seconds, the light reaches Earth. On the day side of the planet, where the Sun is visible in the sky, the change is immediate and impossible to miss. The Sun, that familiar bright disk, suddenly gets brighter, much brighter. In the span of a few heartbeats, it goes from being the normal Sun to being something that seems wrong, that seems impossible. Someone in Sao Paulo, that person eating lunch in the park, looks up and squints. The Sun seems unusually bright today, they think. Did it always hurt this much to have it in their peripheral vision? They look away, blinking, seeing spots in their vision. Around them, other people are reacting similarly, shielding their eyes, moving into shade, wondering if something's wrong with the light today. Something is very wrong with the light today. The brightness continues to increase. Within 30 seconds, the Sun is noticeably, alarmingly brighter than it should be. It's not just uncomfortable to look toward, it's impossible. Even with your back to it, even in the shade, the reflected light is intense enough to make you squint. The sky, normally that comfortable blue, is taking on a strange, washed-out quality. Colours seem oversaturated and wrong. People pull out their phones to check the news, to see if anyone else is experiencing this. But phones are starting to behave strangely. Satellites that relay communications are being bombarded with radiation. GPS signals are getting fuzzy, then failing entirely. The internet, that vast global network that depends on satellites and long-distance communication, is developing gaps. Someone tries to call their family. The call doesn't go through. They try again. Still nothing. Around the world, as the day side of Earth rotates beneath this intensifying light, communications are failing. It's not dramatic. Phones don't explode or anything. They just stop working reliably. Calls drop. Data connections fail. The vast technological infrastructure of modern civilization starts to show cracks. And the light keeps getting brighter. At 1 minute after the light arrives, the sun is hundreds of times brighter than normal. People who are outside are moving inside, driven by instinct, by the discomfort of light, so intense it's starting to feel like heat on exposed skin, because it is heat. The infrared radiation is intense enough to be felt. It's like standing too close to a bonfire, except the bonfire is 93 million miles away. Windows that face the sun are becoming unpleasantly warm to the touch. Plastics left in direct sunlight are beginning to soften. Paint on cars is starting to bubble. These are the first minor physical effects, but they're harbingers of worse to come. The plants are the first to show signs of distress at the cellular level. The chlorophyll molecules in leaves, which normally absorb light for photosynthesis, are being overwhelmed. There's such a thing as too much light, and we've passed that threshold. The molecular machinery that converts photons into chemical energy is being damaged by the sheer intensity. Leaves are beginning to bleach, losing their green color as the chlorophyll breaks down. Animals are instinctively seeking shelter. Birds that were flying are landing looking for cover. Dogs are whimpering, pressing themselves into dark corners. Cats, never fond of unexplained changes, have universally decided that under the bed is the only reasonable place to be. Even insects are behaving strangely, as if they sense something fundamentally wrong with the world. And humans are beginning to panic, because the sun shouldn't do this. The sun is supposed to be reliable. It's supposed to be predictable. It's been rising and setting every day for as long as anyone can remember. For as long as human civilization has existed. For billions of years before that, the sun doesn't change. The sun doesn't suddenly get brighter. Except now it has. Scientists at observatories, those who have equipment pointed at the sun, are seeing things that make no sense. The sun's spectrum is all wrong. The radiation levels are impossible. Some have made the connection. This is a supernova spectrum. But that can't be right. Our sun can't go supernova. It's not massive enough. It's not old enough. This shouldn't be possible. But, impossible or not, it's happening. At 2 minutes after the light arrives, the sky on the day side is no longer blue. It's a pale, almost white colour washed out by the intensity of the light. Shadows are incredibly sharp, etched in stark contrast. Everything is too bright, painfully bright. The kind of brightness where you can't even keep your eyes open outside, where even indoors with curtains drawn, the light leaking around the edges is still uncomfortably intense. The UV radiation is now reaching the surface with full force. The ozone layer, which normally filters out most of this harmful radiation, is being destroyed faster than it can regenerate. Without that protection, UV photons are hitting exposed skin, causing damage at the cellular level. People who were outside when the light arrived are beginning to develop what looks like severe sunburn, but developing far faster than any normal sunburn. Within 5 minutes, exposed skin is red, painful, blistering. The DNA in their cells is being damaged by the UV radiation, broken apart by high-energy photons. Some of this damage will be repaired by cellular mechanisms, but not all of it, not at this intensity. This is radiation exposure on a scale that human biology never evolved to handle. Power grids are starting to fail. The electromagnetic pulse that accompanied the light has induced currents in long-distance power lines overloading transformers. In some regions, Automatic protections kick in and shut down the grid before permanent damage occurs. In others, transformers burn out, start fires. The lights go out in city after city as the grid destabilizes. Without power, air conditioning fails just as temperatures are starting to rise. Refrigerators stop working. Hospitals switch to backup generators, if they have them, if they're working, if they weren't also damaged by the electromagnetic pulse. At 5 minutes after the light arrives, people on Earth's dayside are facing a new, terrifying reality. The sun has changed. The comfortable, reliable sun that's been humanity's companion for all of history has become something else, something bright and terrible and wrong. And on the night side, people are watching their phones go dark, their internet connections fail, their satellite TV cut out, and they're wondering what's happening on the other side of the world. They're seeing strange lights in the sky from atmospheric effects, from charged particles, from the edge of that incredible brightness over the horizon. In a few hours, as Earth rotates, they'll find out firsthand. They'll emerge from the protective shadow of their own planet into that overwhelming light. But for now, in these first minutes after the light arrives, the dayside is experiencing the first shock of a catastrophe that's only just beginning. The neutrinos have come and gone, barely noticed except by specialized detectors. The light has arrived and is bathing the planet in radiation that was never meant for Earth. And somewhere in space, invisible to us, moving at a measurable fraction of the speed of light but still taking days or weeks to arrive, the actual physical matter of the sun is on its way, the shock wave, the blast wave, the stellar material that was once the surface of our sun, now heated to millions of degrees and travelling outward like cosmic shrapnel. Those first 8 minutes of grace are over. Earth knows now, and knowing changes everything. So we've seen the light arrive. We've watched as Earth's dayside was bathed in radiation far more intense than anything it was designed to handle. We've seen the first minutes and hours of this impossible catastrophe. But here's the thing about supernovae. The light is just the opening act. The real mass of the star, the actual physical matter, is still on its way. And it takes a while to get here. Light travels at, well, the speed of light. About 186,000 miles per second. Nothing in the universe goes faster. But matter is bound by more practical limitations, even when it's been blasted outward by the most powerful explosion a single star can produce. Even when it's moving at a significant fraction of light speed, it's still slower than light, sometimes considerably slower. The material from our exploded sun is travelling outward at various speeds. The innermost layers, the ones that got the full force of that rebound off the collapsed core, are moving at perhaps 10% the speed of light. That's incredibly fast, about 67 million miles per hour, but it's still 10 times slower than light. The outer layers, which were further from the centre and got a less intense push, might be moving at only a few percent of light speed. Let's do some math, shall we? Earth is about 93 million miles from the Sun. If the blast wave is moving at 10% of light speed, it will take about 10 times as long to reach us as the light did. The light took 8 minutes, so the blast wave? About 80 minutes. An hour and 20 minutes. But that's for the fastest material. The average ejecta, the stellar debris, the actual physical matter of what used to be the Sun, is probably moving at more like 5% of light speed, which means it might take 3 hours to reach us, or 6 hours for the slower material, or even longer for the very outermost layers. So we have this period, this strange interval between the light arriving and the matter arriving, where Earth is experiencing the radiation effects, but not yet the physical impact. It's a bit like seeing lightning before you hear thunder. You know something's coming, you just don't know exactly when it will arrive. What has Earth been experiencing during this waiting period? Well, let's say it's been a few hours since the light arrived. The situation on the day side has gone from bad to worse to catastrophic. The temperature has continued to climb. That heat we talked about, that infrared radiation, it's relentless. The surface temperature in direct sunlight has risen dramatically. We're talking hundreds of degrees now. Hot enough that water boils. Hot enough that plants aren't just wilting, they're combusting. Forests are catching fire spontaneously. Grasslands are burning. Anything flammable that's in direct sunlight is starting to smoke, char, ignite. The oceans are behaving in ways they never have before. The surface layer is heating rapidly, creating enormous amounts of steam. If you could see the planet from space, if any satellites were still working, which most aren't, you'd see the day side shrouded in vast clouds of steam, obscuring the surface below. The ocean is essentially boiling, at least at the surface. The deeper water is still cool, protected by the sheer thermal mass of all that water, but the surface is a roiling, steaming chaos. And the atmosphere is changing too. The upper atmosphere has been heated to extreme temperatures by absorbing all that high-energy radiation. Some of it has heated enough to reach escape velocity. Earth is literally losing atmosphere to space, bleeding air molecules into the void. The atmosphere isn't gone yet, not even close, but it's being eroded, like a sandcastle being worn away by waves, except the waves are made of radiation. The ozone layer is completely destroyed now. There's no protection at all from UV radiation. Any DNA exposed to this light is being systematically shredded. Any organism on the surface, any plant or animal or microbe, is taking damage at the molecular level. Life on the day side is having what you might call a very bad day. On the night side, things are relatively better, though better is a relative term. They're not experiencing the direct radiation. The mass of Earth itself is shielding them, but they're not unaffected. The atmosphere is connected, and the heating on the day side is creating massive weather patterns, unprecedented winds as hot air rises, and cooler air rushes in to replace it. Storms unlike anything in recorded history are forming. And perhaps worst of all, they know what's coming. As Earth rotates, the night side will become the day side. In a few hours, they'll rotate around to face that terrible brightness. There's no escape. You can't outrun planetary rotation. But before Earth rotates enough to expose the night side to direct light, something else is going to happen. The blast wave is going to arrive. Let's say it's been about 2 hours since the light reached Earth. The fastest material from the explosion, that innermost layer travelling at 10% of light speed, is getting close now, very close. It's crossed almost the entire distance between where the Sun used to be and where Earth is now. If we had any functioning telescopes, if we could observe the space between Earth and that expanding remnant, we'd probably see nothing. Space is dark, and stellar material racing toward you doesn't necessarily light up in visible wavelengths. But our instruments would detect it. We'd see the X-rays it's emitting. We'd detect the magnetic fields it's carrying. We'd know it was coming. We'd have a few minutes of warning, maybe 10 minutes, 15 if we're lucky. Time enough to know that something is about to hit us, but not enough time to do anything meaningful about it. And then it arrives. The first material to hit Earth is plasma, ionized gas, heated to millions of degrees, travelling at a significant fraction of the speed of light. It hits the upper atmosphere first, of course. That's how these things work. And the collision is energetic. Imagine throwing a ball into water. The ball displaces the water, pushes it aside, creates a splash. Now, imagine the ball is made of million-degree plasma, and it's hitting the atmosphere at 67 million miles per hour. The splash is somewhat more dramatic. The upper atmosphere, already heated and thin from hours of radiation bombardment, is hit by this wall of stellar material. Some of it is pushed aside, some of it is heated even further and simply escapes into space. Some of it mixes with the incoming material in complex, violent ways that would take a supercomputer to fully model. The result is that Earth's atmosphere is being stripped away. Not instantly, we're talking about a very large planet and a lot of atmosphere, but rapidly. The air we breathe, the protective bubble that's kept life safe for billions of years, is being eroded like a beach in a hurricane. And it's not just the atmosphere. The blast wave carries magnetic fields with it, tangled and intense. When these hit Earth's own magnetic field, the interaction creates tremendous electrical currents in the upper atmosphere. If the power grids weren't already destroyed, this would certainly finish the job. Anything with a circuit, anything with wires, is subjected to induced voltages that would make a lightning bolt look gentle. The satellites that somehow survived the initial radiation, and there probably aren't many, are destroyed now. The International Space Station, if it's still intact, if the astronauts somehow survive the radiation exposure, is hit by this plasma wall. The station was never designed for this. Nothing built by humans was designed for this. The outcome is not good. On the ground, people experience this as a sudden, violent wind, but it's not wind in the normal sense, moving air in the lower atmosphere. This is the atmosphere itself being pushed, compressed, heated. The pressure wave from the blast hits the surface. Buildings shake. Windows that somehow survived the heat now shatter from the pressure wave. Trees that were still standing are knocked flat. It's like a hurricane, except it hits everywhere simultaneously and with far more force. The blast wave isn't following weather patterns or being shaped by geography. It's coming from above, pressing down, driven by the impact of stellar material on the atmosphere. And with the atmosphere being compressed and heated, the temperature spikes even higher. We're already well above the boiling point of water in many places. Now we're reaching temperatures where metal softens, where rock begins to melt. The surface of the planet is being subjected to heat that normally only exists inside a furnace or a volcano. The oceans, already steaming, are now being physically pushed by the pressure of the blast wave hitting the atmosphere. Enormous waves form, not from wind on the surface, but from the entire body of water being literally compressed by atmospheric pressure tsunamis of superheated water race across the oceans, carrying steam and heat. And here's where we need to talk about what happens to the surface of the planet when you subject it to these conditions. Because Earth's surface, for all its stability, is really just a thin crust floating on a molten interior. We don't think about it that way most of the time because the crust is solid and stable and we live our entire lives on it. But it's thin. The crust is only a few miles thick under the oceans, maybe 25 miles thick under continents. Beneath that is the mantle, which is hot and plastic and capable of flowing over geological timescales. Under normal conditions, the crust stays solid because it's constantly radiating heat into space and being cooled by the atmosphere and oceans. But now the surface is being heated from above, intensely. The rock that makes up Earth's surface is heating up, softening, beginning to melt. We're not talking about the entire crust melting. That would require sustained heating over a much longer period. But the surface, the top few feet or meters, that's definitely melting. If you could see the surface of the dayside now, it would look like a vast sea of glowing molten rock. Magma flows that aren't coming from volcanoes, just from the sheer heat being applied from above. Any structure still standing is now sinking into molten rock. Cities, built of concrete and steel, are being reduced to their component elements. The concrete is breaking down in the heat. The steel is melting. Everything humanity has built, all of our architecture and infrastructure and civilization, is being erased, not destroyed in the sense of being broken into pieces, but actually melted, reduced to its constituent atoms, losing all structure and form. And the blast wave keeps coming. It's not a single impact. It's an ongoing barrage. The explosion sent out waves of material at different speeds, and they're arriving in sequence. After the fastest material hits, there's the slightly slower material, then the slower material after that. Each wave adds more heat, more pressure, more violence to what's already an apocalyptic situation. Deep underground, there might be places where the heat hasn't fully penetrated yet. Cave systems, deep mines, subway tunnels far below the surface. These might still be survivable in terms of temperature, but the atmosphere is being stripped away. And without an atmosphere, there's no air to breathe. Any survivor in a deep shelter would find themselves in a very strange situation, protected from the heat by layers of rock, but suffocating as the air pressure drops and the oxygen content plummets. And even if they could somehow survive the loss of atmosphere, if they had oxygen tanks, sealed environments, there's the problem of what comes next. Because Earth isn't just being heated and stripped, it's being fundamentally changed. The blast wave is carrying material from the sun, heavy elements forged in the explosion, radioactive isotopes, exotic compounds. This material is mixing with Earth's atmosphere and surface, contaminating everything. The planet is being seeded with radioactive material that will remain dangerous for thousands of years. Even if the heat eventually subsides, even if the atmosphere somehow rebuilds, the surface will be poisonous. Living here will require dealing with radiation levels that would make a nuclear waste site look pristine. Let's talk about the other planets, because Earth isn't the only world in the line of fire. Mercury, much closer to the Sun, was hit by the light about 3 minutes after the explosion. The blast wave reached it maybe 20 or 30 minutes later. Mercury, being small and having almost no atmosphere, offered no resistance. The surface temperature spiked to extreme levels. Rock vaporized. Mercury might not exist as a coherent planet anymore. It might have been simply blown apart, reduced to a cloud of rocky debris. Venus, with its thick atmosphere of carbon dioxide, fared slightly better. The atmosphere absorbed some of the impact, though better is relative. The surface of Venus, already hot enough to melt lead, got even hotter. The atmospheric pressure spiked as the atmosphere was compressed and heated. Venus became even more of a hellish world than it already was, if such a thing is possible. Mars, further out than Earth, has a few more hours before the blast wave arrives. The light has already reached it. It's experiencing the radiation effects, but it has a thinner atmosphere than Earth, less protection. When the blast wave hits, Mars will lose what little atmosphere it has. The red planet will become even more barren, even more hostile to life. The gas giants, Jupiter, Saturn, Uranus, Neptune, are far enough away that it will take hours or even days for the blast wave to reach them. They'll weather it better than the rocky inner planets, simply because they're so massive and have such deep atmospheres. The outer layers might be stripped away, but the planets will survive. They're moons, though. The moons might not be so lucky, especially the ones facing toward the sun when the explosion occurred. And poor Pluto, out in the cold darkness of the outer solar system, is going to be in for a surprise in a few days or weeks when the blast wave finally reaches it. For a brief moment, its frozen atmosphere will thaw and expand as the wave of heat passes. Then, As the heat dissipates, it will freeze again. Pluto will experience a bizarre, violent summer and then return to its usual frozen state. But we're focusing on Earth because that's where we are, where we've always been, where all of human history has unfolded, and Earth, after being hit by this blast wave, is no longer recognizable. The blue planet, the water world, the oasis of life in a sterile solar system, it's gone. What's left is a scorched, airless rock, its surface molten, its oceans vaporized, its atmosphere stripped away. The planet itself still exists. The blast wave is powerful, but not powerful enough to destroy an entire planet. The core is still there, still molten. The mantle is still there, still hot. Even the crust beneath that melted surface layer is still intact. But the Earth we knew, the Earth that supported life, that had blue oceans and green forests and cities and civilization and all the complex, beautiful variety of life that took billions of years to evolve, that Earth is gone. And somewhere in the space where our sun used to be, there's now a rapidly expanding cloud of stellar material, a supernova, remnant glowing with the heat of creation, seeded with heavy elements that will one day form new stars and planets. Somewhere in that cloud, at the very center, there's a neutron star or black hole, the crushed remains of the core. But we're here, on this planet, in this moment of catastrophe, watching our world be unmade by forces we never could have prevented, experiencing destruction on a scale that makes our words seem inadequate. The blast wave has arrived. Earth has been struck, and nothing will ever be the same. And nothing will ever be the same. It's natural, when contemplating catastrophe, to ask about survival. It's what we do as humans. We look for the escape route, the safe harbour, the way through. And so the question arises, in this scenario we're imagining, could anything survive? Is there anywhere on Earth or anywhere in the solar system where life might persist? The short answer, unfortunately, is no. Not really. Not in any meaningful way. This is, without exaggeration, the most unsurvivable scenario we've explored in these cosmic journeys together. The sun disappearing, at least you have time to try to adapt, to move underground, to build heated shelters. But the sun exploding, the sheer violence of it, the intensity of the radiation, the heat, the physical blast wave, it's simply too much. But let's explore the question anyway, because understanding why things can't survive helps us appreciate the forces involved. And who knows? Maybe there are some extremely stubborn microbes out there that might prove us wrong. Life has surprised us before. Let's start with the surface, because I think we can all agree at this point that nothing on the surface survives. We've melted the crust. We've boiled the oceans. We've stripped away the atmosphere. If you're a tree, a bird, a human standing on the surface when this happens, your survival time is measured in seconds, maybe minutes if you're very unlucky, and it takes that long for the heat to reach you. There's no shelter that helps, no building strong enough. You could be in a bank vault, in a bomb shelter, in the most reinforced structure humanity has ever built, and it wouldn't matter. The heat would penetrate, the radiation would penetrate, the structure itself would melt. Steel has a melting point of about 2,500 degrees Fahrenheit. We're exceeding that. Concrete breaks down at high temperatures. Glass obviously melts. There's nothing you could build on the surface that would protect you. So the surface is out. What about underground? This is where things get slightly more interesting, though interesting still doesn't mean survivable. The deeper you go underground, the more insulation you have from what's happening at the surface. Rock is actually a pretty good insulator. Heat takes time to penetrate through solid stone. If you were deep enough underground when the blast wave hit, you might survive the initial heat. The question is, How deep is deep enough? Let's think about this. The surface is being heated to temperatures that melt rock. That heat will conduct downward through the crust, but it takes time. Heat doesn't travel instantly through solid material. It diffuses, spreads, gradually equalizes. If you're a mile down, you might have hours before the heat reaches you. 2 miles down? Maybe a day or two. There are some truly deep places on Earth. The deepest mine is about 2.5 miles down. There are natural cave systems that go deeper still. And of course, the Earth's crust itself extends down for many miles. You could theoretically be 5 or 10 miles down if you had some way to get there and survive at those depths. At those depths, you'd be protected from the immediate heat. The rock above you would absorb the energy, would heat up gradually rather than instantly. You might have time, days, even weeks, before the temperature in your deep shelter became unbearable. But here's the problem. You still need to breathe, and the atmosphere is gone. Even if heat hasn't reached your deep shelter, the air you're breathing came from the surface. It's part of a connected system, and that system has been disrupted rather severely. The atmospheric pressure would drop as the atmosphere is stripped away. If you're in a sealed environment, this might not immediately affect you. Submarines and spacecraft are sealed from their external environment all the time, but eventually your air supply runs out. You need fresh air, recycled air, something. And with the surface uninhabitable and the atmosphere gone, there's no way to replenish it. Let's say, optimistically, that you're in a deep shelter with a really good air recycling system, something designed for long-term habitation, maybe a bunker built during the Cold War with modern life support technology. You could survive for weeks, months. Eventually, though, something in the system would fail, or you'd run out of food, or you'd go quietly mad from the isolation and the knowledge of what's happened to the world above you. And even if you somehow solved all those problems, even if you had years of supplies and perfect recycling systems and unshakable mental fortitude, you'd still be trapped because the surface isn't going to become habitable again. Not in your lifetime. Probably not in thousands of lifetimes. The heat will eventually penetrate to your depth. The radiation from the radioactive isotopes scattered across the surface will persist for millennia. There's no coming back from this. So deep shelters buy you time, but they don't buy you survival. Not really. What about the deep ocean? We mentioned earlier that hydrothermal vent communities don't depend on the sun. They get their energy from volcanic vents, from the heat of Earth's interior. Could they survive? This is actually one of the more interesting questions, because these communities really are independent of surface conditions. A supernova could happen, and the tube worms wouldn't even notice. No sunlight reaches them anyway. No UV radiation penetrates to those depths. They live in eternal darkness under crushing pressure, and they're fine with that. The problem is the ocean. The ocean's surface has boiled. That's a lot of energy being pumped into the water. And while the deep ocean is cold and vast and has enormous thermal mass, it's still connected to the surface. The heat will penetrate downward. Slowly, yes. Water is a good heat sink and there's a lot of it, but it will penetrate. The hydrothermal vent communities might survive for a while, maybe months, maybe even years, but the ocean is heating up. The pressure is changing as water evaporates. The chemistry is changing as all that surface material, vaporized rock, stellar debris, exotic compounds, mixes into the water. Eventually, even those deep refuges will become uninhabitable. And here's another problem. Earth's volcanic activity is ultimately driven by internal heat, but it's moderated by surface conditions. With the surface melted and the oceans boiled away, the heat balance of the entire planet is disrupted. volcanic activity might actually increase as the planet tries to shed excess heat, or it might decrease if the changing pressure conditions affect magma formation. Either way, those hydrothermal vents might not keep venting. The ecosystems built around them would collapse. So even the deep ocean communities, independent as they are, probably don't survive long term. What about microbes? Because microbes are remarkably tough. We find them in the most extreme environments on Earth. Deep underground, where they live off of chemical reactions in the rock in boiling hot springs, in Antarctic ice, in the upper atmosphere, in nuclear reactors, for crying out loud. Life finds a way, as a certain film character once said, and microbes are very good at finding ways. There are microbes that live miles underground, feeding off of hydrogen produced by radioactive decay in rocks. They don't need sunlight, they don't need oxygen, they don't even need organic matter from the surface. They're completely independent, living in tiny pockets of water in fractured rock, reproducing perhaps once per century because resources are so scarce, but surviving nonetheless. Could those microbes survive a supernova? Maybe, just maybe. If they're deep enough, if they're in a stable enough environment, if the heat takes long enough to reach them, they might persist. Not thrive, certainly. The planet as a whole is being subjected to trauma that will affect even the deep subsurface. But microbes are patient, they're resilient. If anything survives this, it's them. But, and this is a large but, even if they survive, what have they survived to? A planet with no atmosphere, no oceans, a surface that's molten rock slowly cooling over thousands of years. The underground environment they depend on might be stable for now, but Earth is changed. The heat flow patterns are different, the geological processes are disrupted. Their little refugees might not stay habitable forever. And even if some microbes do survive for thousands or millions of years, is that really survival in any meaningful sense? They're not going to repopulate the planet. They're not going to evolve into complex life again. They're just going to persist in their little pockets of water and rock, isolated and unchanging, until eventually even those refuges fail. Let's think about the other planets for a moment, because Earth isn't the only place in the solar system where we've discovered or theorized about life. Mars has no confirmed life, but there's speculation about microbes deep underground, possibly living off of subsurface water and chemicals. If they exist, would they survive? Mars is further from the Sun than Earth, so the blast wave arrives later and with less intensity. But Mars also has even less atmosphere than Earth started with. When the blast wave hits, Mars loses what little air it has entirely. Any surface ice is vaporized. The planet is scoured by radiation. Deep underground, Martian microbes, if they exist, might have a slightly better chance than Earth life simply because Mars is further away. But they face the same problems: eventual heat penetration, disrupted environment, no possibility of recolonization of the surface. Europa, one of Jupiter's moons, has a subsurface ocean beneath miles of ice. Some scientists think this ocean might harbor life. Europa is so far from the Sun that the blast wave will take hours to arrive and will be much less intense by the time it gets there. The thick ice shell would provide excellent protection. So Europa life, if it exists, might actually survive. The ice shell might melt or crack, but the ocean beneath would be protected. The tidal heating from Jupiter that keeps the ocean liquid would continue. That's not dependent on the Sun at all. In our entire solar system, Europa might be the one place where life survives relatively intact. Of course, there's a rather significant asterisk here. We don't actually know if Europa has life. It's speculation based on having liquid water and energy sources. But if it does, and if our supernova scenario happened, Europa might end up being the sole inheritor of life in our solar system. Strange to think about, life persisting not on Earth but on a small moon of Jupiter, in a dark ocean beneath kilometers of ice. Let's talk about technology for a moment. Could we, with our technology, create any kind of survival shelter? If we knew the sun was going to explode, which we would, because we'd see the signs of a massive star approaching the end of its life, could we prepare? The answer is probably not in any way that matters. We could build bunkers, sure. Deep underground facilities with years of supplies. We could build them on the far side of the planet, the night side, to buy ourselves a few extra hours before Earth's rotation brings us around to face the supernova. We could even perhaps evacuate to space stations or moon bases, putting the bulk of the moon between us and the sun. But these are temporary measures. You're not surviving the explosion, you're just delaying the inevitable. Space stations need supplies. Moon bases need supplies. Those supplies come from Earth, and Earth is now a molten, airless rock. The moon itself will be bombarded with radiation, and possibly by physical debris. It's not a safe haven, it's just slightly less immediately deadly than being on Earth. You could, in theory, try to leave the solar system entirely. Build generation ships and flee to another star. But building generation ships capable of supporting humans for the decades or centuries it would take to reach another star system, that's science fiction levels of technology. We don't have that. We're not close to having that. And even if we did, how many people could you save? A few thousand? A few million if you were very optimistic and had incredible resources, out of 8 billion people on Earth. You're not saving humanity. You're saving a remnant. A tiny seed population that would have to survive unimaginable hardship in the hopes of finding another habitable world. The cold reality is that if the sun exploded, we would not survive as a species. Not on Earth, not in space, not anywhere in the solar system. The violence is simply too immediate, too overwhelming, too complete. And here's where I want to pause and remind you of something important. This can't happen. Our sun cannot explode as a supernova. It's not massive enough. What we're describing is impossible for our particular star. This is imagination, a way of understanding the forces involved in stellar explosions, a way of appreciating the power that exists in the universe. But somewhere in our galaxy right now, there might be a planet orbiting a massive star that is approaching the end of its life. And on that planet, if there's life, if there's intelligence, they might be looking up at their star and wondering what comes next. For them, this isn't imagination. This is their future. They might have a few million years of warning if their star is following the standard path to supernova. That's a lot of time to prepare, to develop technology, to potentially leave their planet and find somewhere else to live. Or they might have much less warning if their star is one of the ones that explodes relatively young. Either way, they face a challenge that makes our worst catastrophes look trivial. They have to leave their world or die. There's no third option. And if they do leave, they have to accept that their home planet, the world where their species evolved, where all their history took place, where everything they've ever known exists, that world is going to be destroyed. That's a loss almost impossible to comprehend. We humans have never had to face it. We've had disasters, yes, floods, fires, earthquakes, plagues, but the planet itself has always persevered. We've always been able to rebuild. But a supernova? There's no rebuilding from that. So, could anything survive a supernova at Earth's distance? A few microbes, maybe, deep underground, for a while, and that's about it. This is extinction, not just of a species or a biosphere, but of a world. Total, complete, final. And that makes us appreciate once again the remarkable gift we have. We orbit a gentle star, a stable star, a star that won't explode, that will shine steadily for billions of years yet, that gives us time, so much time, to grow and learn and explore and become whatever we might become. We have the luxury of thinking about supernovae as interesting physics rather than imminent threats. That's not a small thing. That's everything. We've spent considerable time exploring destruction, the violence of the explosion, the devastation to Earth, the impossibility of survival. It's been rather bleak, hasn't it? But here's where our story takes a turn towards something more hopeful, more beautiful, because supernovae aren't just about destruction, they're also about creation. In fact, they're essential to creation. Without supernovae, without the violent death of massive stars, the universe would be a much simpler, much emptier place. And you, yes, you listening to this right now, wouldn't exist. Let's talk about what supernovae create. First, and most fundamentally, they create elements, heavy elements, the building blocks of complexity. And to understand why this matters, we need to take a brief detour into the history of the universe. When the universe began about 13.8 billion years ago, it started with the Big Bang. In those first moments, the universe was unimaginably hot and dense. As it expanded and cooled, the first atoms formed. But here's the thing, the early universe was remarkably simple. It was almost entirely hydrogen, with a bit of helium and trace amounts of lithium. That's it. 3 elements. The periodic table, in those early days, was very short. Everything else, every element heavier than lithium, had to be made later, made inside stars, and for the heaviest elements, made inside exploding stars. We talked about this a bit in our first chapter, but let's go deeper now. Inside a star, nuclear fusion combines lighter elements into heavier ones. Hydrogen fuses into helium, helium into carbon, carbon into oxygen. This process releases energy, which is why stars shine. But there's a limit to how far this can go. For normal stars like our Sun, the limit is around carbon and oxygen. We don't have enough mass, enough gravitational pressure to fuse heavier elements. When our Sun dies, it will have created some carbon and oxygen, and it will shed these elements into space as a planetary nebula. But that's as far as it goes. Massive stars can go further. They have enough pressure, enough heat to continue the fusion chain. They make neon, magnesium, silicon, sulfur. They make all the way up to iron. But iron, as we discussed, is the end of the line. You can't fuse iron and get energy out. Fusing iron requires energy input, so iron builds up in the core until the star collapses and explodes. But here's the beautiful part. When the star explodes, when all that energy is released in these few seconds of incredible violence, conditions become extreme enough to create elements heavier than iron gold. Platinum, uranium, thorium, all the lanthanides and actinides, every heavy element on the periodic table. These elements are created in the supernova itself, in that moment of explosion. They're forged in the incredible heat and pressure, created through rapid neutron capture, a process where atomic nuclei are bombarded with so many neutrons so quickly that they have no choice but to absorb them and transform into heavier elements. And then, once created, these elements are scattered into space. The explosion blasts them outward, mixing them into the interstellar medium, the gas and dust that exists between the stars. And there they wait, these newly minted atoms, drifting in space, until gravity begins to pull them together again to form new stars and planets. Our Sun is what astronomers call a third-generation star. That means it formed from gas that had already been enriched by previous generations of stars. The cloud that collapsed to form our Sun contained not just hydrogen and helium, but heavier elements too: carbon, oxygen, silicon, iron, all the elements that make rocky planets possible. And when Earth formed from the disk of material around the young Sun, it incorporated these heavy elements. The iron in our core came from ancient supernovae. The silicon and oxygen in our rocks came from ancient supernovae. The calcium, the nickel, the sulfur, all of it forged in stellar explosions billions of years before our solar system even existed. And life? Life depends on heavy elements. Carbon is the basis of all organic molecules. Nitrogen and oxygen are essential. Phosphorus, sulfur, iron, all critical to biology. Without supernova, without the creation of these elements, life as we know it couldn't exist. We'd have a universe full of hydrogen and helium, and that's just not enough to build anything interesting. So when we look at the periodic table, when we see all those elements heavier than lithium, we're looking at the products of stellar nucleosynthesis. And for the heavy ones, everything beyond iron, we're looking at the products of stellar death, violent, explosive, catastrophic death that scattered atoms across light years of space. You're made of stardust. Carl Sagan said this, and it's become something of a cliché, but it's literally true. The atoms in your body were forged in the cores of stars and in the explosions of stars. The iron in your blood, carrying oxygen to your cells, that iron was created in a supernova billions of years ago. The calcium in your bones, the carbon in your DNA, the oxygen you're breathing right now, all of it came from stars that lived and died before our Sun was born. In our scenario, our exploded Sun is creating these heavy elements right now. In the incredible heat and pressure of the explosion, neutron capture is occurring, new nuclei are forming, the periodic table is being populated with fresh atoms. These atoms will expand outward with the debris cloud, will mix with the interstellar medium, and perhaps in a few billion years will be incorporated into a new generation of stars. So even as Earth is destroyed, even as our planet and everything on it is reduced to molten rock and scattered atoms, the explosion is simultaneously creating the building blocks for future worlds. It's destruction and creation happening simultaneously, two sides of the same cosmic process. Let's talk about what's left behind at the center of the explosion, because when a massive star explodes, the core doesn't entirely disappear. It collapses, remember, crushed by gravity into an incredibly dense object. And what that object becomes depends on the mass of the original star. For stars about 8 to 20 times the mass of our Sun, the core collapses into a neutron star. This is one of the strangest objects in the universe. Imagine taking something with more mass than our entire Sun and compressing it into a sphere about 10 miles across. That's a neutron star. The density is incomprehensible. A teaspoon of neutron star material would weigh about as much as Mount Everest. That's not an exaggeration or a metaphor. That's the actual density. Matter is compressed so tightly that protons and electrons are forced together to make neutrons, and those neutrons are packed together with essentially no space between them. The surface gravity is so strong that if you drop something from a height of 1 meter, it would hit the surface at about 7 million kilometers per hour. The surface itself is probably crystalline, a lattice of iron nuclei, the strongest material in the universe. And beneath that surface there are layers of increasingly exotic forms of matter, possibly including superfluids and exotic particles that can't exist anywhere else. Neutron stars also spin fast. Some of them rotate hundreds of times per second, and they have magnetic fields trillions of times stronger than Earth's. If a neutron star got close enough to Earth, and by close enough I mean tens of thousands of kilometers, its magnetic field would be strong enough to disrupt the molecular bonds in your body. You would quite literally cease to be structurally stable. Some neutron stars are pulsars. They emit beams of radiation from their magnetic poles, and as they spin, these beams sweep across space like a lighthouse. If the beam happens to point toward Earth, we detect regular pulses, timed with incredible precision. The first pulsar discovered was so regular that astronomers briefly wondered if it might be an alien signal. It wasn't, of course, just a rapidly spinning neutron star. But for a moment, the universe seemed even stranger than it actually is. In our scenario, if our sun somehow had the mass to go supernova, which it doesn't, but we're imagining, it would probably leave behind a neutron star. This neutron star would be roughly where the sun used to be, though the explosion would have given it a kick, sent it moving through space at high velocity. It would be incredibly hot at first, cooling slowly over millions of years, and it would be all that's left of our sun, a city-sized sphere of exotic matter, the compressed remains of a star that once provided light and warmth to an entire planetary system. For even more massive stars, those above about 20 solar masses, the core collapse goes even further. The neutron star isn't stable. Gravity overwhelms even neutron degeneracy pressure, and the collapse continues. The core shrinks past the point of no return, past the event horizon, becoming a black hole. A black hole is even stranger than a neutron star, if such a thing is possible. It's a region of space-time where gravity is so strong that nothing, not even light, can escape. The matter that formed it has collapsed to a singularity, a point of infinite density, where our understanding of physics breaks down completely. Around the singularity is the event horizon, the point of no return. Cross that boundary, and you can never come back. You'd be pulled toward the singularity by tidal forces so strong they'd tear you apart at the molecular level, a process affectionately called spaghettification by physicists, because apparently they do have a sense of humour. Our sun isn't massive enough to leave behind a black hole. Even in our imaginary scenario, 15 solar masses would probably leave a neutron star, but the most massive stars, those giants 30 or 50 or 100 times the sun's mass, when they explode, they leave black holes behind, and those black holes can grow, can accrete matter, can merge with other black holes, eventually becoming the supermassive black holes that sit at the centers of galaxies. So supernovae create both the lightest elements on the periodic table's heavy end and the densest objects in the universe. Not bad for a process that only takes a few seconds. Now let's talk about the nebula, the expanding cloud of debris, because this is perhaps the most visually spectacular part of what a supernova creates. As the stellar material expands outward, it stays hot for quite a while. It's glowing, not from fusion, but from the energy of the explosion itself and from the decay of radioactive isotopes. This glowing cloud is what we call a supernova remnant, and it can be visible for thousands of years. The Crab Nebula is probably the most famous supernova remnant. It's the remains of a star that exploded in 1054 CE. Chinese astronomers recorded seeing a guest star so bright it was visible during the day. That guest star was a supernova, and what's left is a beautiful, complex nebula about 6 light-years across, still expanding, still glowing, still beautiful nearly 1,000 years later. If you look at images of the Crab Nebula, and I encourage you to do so, it's stunning. You see intricate filaments of gas in different colours. Each colour represents a different element, glowing at a specific wavelength. Red is hydrogen, blue-green is oxygen. The whole thing is threaded with magnetic fields, structured by shock waves, illuminated by the pulsar at its center. That's what our sun would leave behind, an expanding nebula glowing in the darkness of space. It would be visible from other stars. Perhaps some alien astronomer on a planet orbiting Alpha Centauri would see a new bright star appear in their sky, would watch it fade over months, would eventually observe it as a nebula through their telescopes, never knowing that this beautiful cosmic cloud was once a star that warmed a planet called Earth. The nebula would expand for thousands of years, gradually cooling, gradually mixing with the surrounding interstellar medium. The shockwave from the explosion would compress nearby gas clouds, possibly triggering the formation of new stars. The heavy elements would spread out, enriching the galaxy with the raw materials for future planetary systems. And eventually, millions of years from now, some of that material would be incorporated into a new generation of stars. A new star would form, perhaps with planets. One of those planets might be rocky, might have water, might develop life. And that life, billions of years later, might look up at their sky and wonder where they came from, never knowing that their atoms were once part of a star called Sol, which exploded and scattered itself across light years, seeding the universe with the elements necessary for their existence. There's a concept in astronomy called the stellar life cycle. Stars are born from collapsing gas clouds. They live by fusing hydrogen into helium. They die, either gently like our sun will, or violently like the massive stars do, and their death enriches the interstellar medium, making the next generation of stars more complex, more metal-rich, more capable of forming rocky planets and complex chemistry. We're part of that cycle. Our atoms have been through it multiple times. They've been in stars before. They've been scattered by supernovae before. They've formed planets before. And they'll do it all again after we're gone, after Earth is gone, after the sun is gone. There's something both humbling and comforting about that perspective. We're temporary. Our planet is temporary. Even our sun is temporary. But we're part of something larger, something cyclical, something that's been happening for billions of years and will continue for billions more. Supernovae destroy worlds, but they also create worlds. They destroy stars, but they also seed new stars. They end life, but they make new life possible. The universe requires both creation and destruction. You can't have one without the other. And supernovae are where that duality is most perfectly expressed, the most violent, destructive events we know of, and simultaneously the most creative, generative processes in the cosmos. In our scenario, Earth is gone. Humanity is gone. The sun has become a neutron star or black hole, surrounded by an expanding nebula. But that nebula contains everything that Earth was made of, plus new elements created in the explosion. It contains the atoms that were once rocks, oceans, atmosphere, the atoms that were once dinosaurs and redwoods and humans. All of it mixed together, indistinguishable now, scattered across light years, but still there, still existing, just in a new form. Matter is conserved. Energy is conserved. Nothing is truly lost, only transformed. And perhaps that's the closest thing to immortality the universe offers. Not that we persist, but that what we're made of persists, gets recycled, becomes something new. The creation that comes from supernovae isn't immediate or obvious. It takes millions of years, billions of years, but it's inevitable. Death feeds life. Destruction enables creation. And the most violent explosion a star can produce is also the most generous gift it can give to the universe, the gift of complexity, of diversity, of the raw materials needed to build a cosmos full of interesting things, including, once upon a time, us. We've spent considerable time imagining an impossible scenario, our sun exploding in a supernova. But here's the wonderful thing about astronomy. We don't have to rely entirely on imagination. We've actually seen supernovae, many of them. And while we've been fortunate enough to observe them from safe distances, these real observations have taught us everything we know about how stellar explosions work. Let's talk about some of the supernovae that humans have witnessed, recorded and studied, because these aren't just abstract physics. These are real stars that really exploded, and we were here to see it happen. The oldest recorded supernova that we know about comes from Chinese astronomical records in 185 CE. Chinese astronomers were meticulous record keepers. They documented celestial events with impressive precision, noting when and where new stars appeared, how bright they were, how long they remained visible. The supernova of 185 CE was described as a guest star in the constellation we now call Centaurus. It remained visible for about 8 months before fading from view. We can't see that supernova anymore, it's long since faded, but we've identified the remnant. It's called RCW86, a shell of expanding gas still moving outward from that explosion nearly 2,000 years ago. Modern telescopes can see it in X-rays and radio waves, can study its structure, can learn about the star that died when the Roman Empire still ruled much of the known world. But perhaps the most famous historical supernova appeared in 1054 CE. This one was recorded by Chinese astronomers, Japanese astronomers, and possibly by Native American observers as well. It appeared in the constellation Taurus, and by all accounts, it was spectacular. Visible during the day for over 3 weeks, bright enough to read by at night, it remained visible to the naked eye for about 2 years before finally fading below the threshold of human vision. We know this supernova as SN 1054, and its remnant is the Crab Nebula we discussed in the last chapter. That beautiful, complex structure of glowing filaments and shock waves, that's what was left behind by the guest star of 1054. At the centre is a pulsar, a rapidly spinning neutron star rotating 30 times per second, emitting beams of radiation that sweep across space like a cosmic lighthouse. Imagine being an astronomer in 1054, looking up at the night sky and seeing something that shouldn't be there, a bright star where no star had been before, and not just any star, one of the brightest objects in the sky. You'd have no framework for understanding what you were seeing, no knowledge of stellar evolution, nuclear fusion, core collapse. It would seem like magic, or divine intervention, or some cosmic omen. The Chinese astronomers called it a guest star, which is rather charming when you think about it, as if the star had come to visit for a while and would eventually leave, which in a sense it did. The visible light faded, and the guest star departed, leaving behind only the nebula that modern telescopes would discover centuries later. In 1572, another supernova appeared, this time in the constellation Cassiopeia. This one was observed by the Danish astronomer Tycho Brahe, and it's now known as Tycho's supernova. Brahe was a careful observer. He had a rather impressive nose made of brass after losing his real one in a duel, which is one of my favourite astronomy facts, and he documented this new star meticulously. Tycho's supernova challenged the prevailing belief that the heavens were unchanging and perfect. According to Aristotelian philosophy, everything beyond the moon was eternal and immutable. But here was clear evidence of change, a new star appearing where none had been before. It was a crack in the old world view, a hint that the cosmos was more dynamic than anyone had imagined. The remnant of Tycho's supernova is still visible today. It's a shell of expanding gas about 13,000 light-years away, still glowing, still carrying evidence of the explosion that destroyed a star before Shakespeare wrote Hamlet. In 1604, another supernova appeared, this time observed by Johannes Kepler. Kepler's supernova, as it's now called, was visible to the naked eye for over a year. It appeared in the constellation Ophiuchus, and like Tycho's supernova before it, it provided evidence that the heavens were not static. What's remarkable is that 1604 was the last supernova visible to the naked eye in our own galaxy. It's been over 400 years, and we haven't seen another one in the Milky Way. There have almost certainly been supernovae in our galaxy since then. Statistics suggest there should be about 2 or 3 per century, but they've happened in parts of the galaxy where dust and distance obscure them from our view. We've been somewhat overdue for a good, visible galactic supernova for quite some time now. Fast forward to 1987, February 23rd, 1987 to be precise. An astronomer in Chile named Ian Shelton was photographing the Large Magellanic Cloud, a small satellite galaxy orbiting our own Milky Way, and in his photographs he noticed something unusual. A bright point of light where no bright star had been before. SN1987A had just been discovered, and this one was special. SN1987. A was the first supernova visible to the naked eye in over 380 years. It wasn't in our own galaxy. The Large Magellanic Cloud is about 168,000 light-years away, but it was close enough to study in detail with modern telescopes. For the first time in the space age, with all our satellites and computers and spectroscopes, astronomers could observe a supernova from start to finish. And what they learned was extraordinary. First, they detected the neutrinos. Remember those antisocial particles that barely interact with matter? About 3 hours before anyone saw the visible light, neutrino detectors in Japan and the United States picked up a sudden burst. 24 neutrinos total, arriving over a period of about 12 seconds. 24 doesn't sound like much, but remember, neutrinos rarely interact with anything. For detectors to catch 24 of them, there must have been trillions passing through the Earth. It was the first time neutrinos from a supernova had been detected, and it confirmed the theory of how supernovae work. The core collapse produces a neutrino burst, and that burst carries away most of the explosion's energy. Theory predicted it, and SN1987A proved it. The light curve of SN1987A, the graph showing how its brightness changed over time, matched predictions beautifully. It brightened over several days, peaked, and then gradually faded over months, powered by the decay of radioactive isotopes created in the explosion astronomers could watch in real time, as theory matched observation, as the physics they'd worked out on paper played out in the actual sky. But SN1987, A had surprises too. The star that exploded wasn't quite what astronomers expected. They'd predicted that supergiant stars, huge puffy red stars, would be the ones to explode. But the star that became SN1987A was blue. It had been a red supergiant, but it had contracted and heated up before exploding, for reasons we're still trying to fully understand. The universe, as always, was a bit more complex than our model suggested. Today, over 35 years later, we're still studying SN1987A. The expanding debris cloud has crashed into material that the star shed before it exploded, creating a ring of glowing gas around the central remnant. It's beautiful, and it's teaching us about the late stages of massive stars' lives, about the material they eject, about how supernova remnants evolve. And we're waiting for something else. At the center of that debris cloud, there should be a neutron star or possibly a black hole, the collapsed core of the star. But we haven't seen it yet. The debris is still too thick, too opaque. But eventually, as the cloud expands and thins, we should be able to detect it. When we do, it will be the youngest neutron star ever observed, born in 1987, which is practically yesterday in astronomical terms. Now let's talk about Betelgeuse, because if there's one star that gets astronomy enthusiasts excited about the possibility of seeing a supernova in our lifetime, it's Betelgeuse. Betelgeuse is a red supergiant star in the constellation Orion. It's the bright reddish star that marks Orion's right shoulder, or left shoulder, depending on whether you're looking at Orion from the front or back. Astronomy can be confusing that way. Betelgeuse is huge. If you put it where our Sun is, its surface would extend past the orbit of Mars. It's also relatively close, about 650 light-years away, which is practically in our cosmic neighbourhood, and most importantly, it's the kind of star that will go supernova. It has the mass. It's in the right stage of life. It's approaching the end. The question is when? The answer is, we don't know. Could be tomorrow. Could be 100,000 years from now. Stellar lifetimes in this late stage are unpredictable. Betelgeuse might explode tonight, and we wouldn't see the light for another 650 years, because that's how long it takes light to travel from there to here, or it might have already exploded, and the light is on its way, due to arrive next Tuesday. We literally have no way of knowing. In late 2019 and early 2020, Betelgeuse dimmed significantly. It dropped to about 40% of its usual brightness, and the astronomy world got very excited. Was this it? Was Betelgeuse about to explode? Social media lit up with speculation. Amateur astronomers pointed their telescopes at Orion. Professional astronomers scrambled to get observation time on major telescopes. Spoiler alert, Betelgeuse didn't explode. It turns out the dimming was caused by a cloud of dust the star had ejected, which was blocking our view. A stellar burp, essentially. The star was fine. Well, as fine as a dying supergiant can be, and by mid-2020 it had returned to normal brightness. But the excitement was real, and it was justified, because when Betelgeuse does go supernova, whenever that is, it's going to be spectacular. At 650 light-years distance, Betelgeuse is far enough that we're completely safe. We're well outside the danger zone. The radiation will be harmless, but it will be bright. Incredibly bright. Estimates suggest it could be as bright as the full moon. Imagine that. A point source of light as bright as the moon, visible during the day, casting shadows at night, remaining visible for weeks or months. It would be the astronomical event of a lifetime, of several lifetimes. The last naked-eye supernova was in 1604, and that one wasn't nearly as bright as Betelgeuse will be. This would be something that would dominate the sky, that everyone on Earth would see, that would make the news around the world. Children born during the time Betelgeuse was visible would grow up with stories about the year a new star appeared in Orion. And then, after months of slowly fading, Betelgeuse would be gone. The constellation Orion would be missing one of its most distinctive stars. We'd have to get used to a new shape, a different pattern. Eventually a nebula would become visible there, and that nebula would grace the constellation for thousands of years. But for now, Betelgeuse is still there, still shining, still slowly approaching the inevitable moment when its core will collapse and it will join the ranks of historical supernovae. These real supernovae, from the guest stars recorded by ancient Chinese astronomers to SN 1987A to the potential future of Betelgeuse, have taught us almost everything we know about how stars die. Every supernova we observe adds to our understanding, confirms our theories, or, more excitingly, surprises us with something we didn't expect. We've learned about core collapse, about neutrino bursts, about shock waves and element creation and neutron stars. We've learned about different types of supernovae, the core collapse ones we've been discussing, and also type Ia supernovae, which happen when white dwarfs in binary systems accumulate too much mass and explode. We've learned about supernova rates, about how often they happen in galaxies like ours, about which stars are candidates and which aren't. And we've learnt something else too. We've learned that supernovae, for all their violence, are beautiful. The images we've taken of supernova remnants like the Crab Nebula, the Veil Nebula, the remnants of historical supernovae, they're stunningly gorgeous complex structures of glowing gas, threaded with magnetic fields, illuminated by shock waves and radiation, painted in colours that represent different elements at different temperatures. The universe, even in its most violent moments, creates beauty, and we, from our safe distance, get to admire it. There's something profound about connecting the physics we've been discussing, the core collapse, the neutron stars, the element creation, with actual historical events. The guest star of 1054 wasn't just theory, it was real. Real astronomers saw it with their own eyes, they described it in their records, and nearly 1,000 years later, we can look at the remnant through telescopes and see the result of that explosion, still expanding, still glowing, still beautiful. When we imagine our sun exploding, we're imagining something that has happened and will happen to countless stars across the universe. We're not inventing physics from nothing. We're applying real, observed processes to our own star, recognizing, of course, that our star can't actually do this, but understanding that somewhere, right now, a star similar to the scenario we've imagined is approaching its final moments. And when that star explodes, if there are observers on a planet somewhere within a few thousand light years, they'll see what the Chinese astronomers saw in 1054, what Tycho saw in 1572, what we saw in 1987, a new star in the sky, a light that wasn't there before, a reminder that the universe is dynamic, that change happens even in the seemingly eternal cosmos. We're part of a universe that creates and destroys, and thanks to the real supernovae we've observed, we understand that process better than any humans before us. We know what we're looking at when we see a guest star. We know what forces are at work, and we know with certainty that our own sun will never do this. We get to observe supernovae as science, as spectacle, as beauty, not as threat. We've talked about what happens when you're too close to a supernova. We've imagined Earth at our actual distance from the Sun, 93 million miles, being devastated by radiation and heat and blast waves. But here's a question that naturally arises. How far away do you need to be safe? What's the safe distance from a supernova? It's a more complicated question than it might seem because safe is a relative term. Safe enough to survive, safe enough to avoid radiation damage, safe enough that your day isn't noticeably affected. These are all different thresholds. Let's think about this systematically, starting from the danger zone and working our way outward to safety. Within about 50 light years of a supernova, you're in what we might call the kill zone. This is the distance at which the radiation, primarily the gamma rays and X-rays, would be intense enough to completely sterilize a planet we're talking about, atmosphere stripped away, ozone layer destroyed, surface life extinguished. If Earth were 50 light years from a supernova when it exploded, the outcome would be similar to what we've been imagining, just slightly less intense. Still completely unsurvivable, just with marginally less melting. Between 50 and 100 light years, things are still very bad, but not quite as immediately catastrophic. The radiation would severely damage the atmosphere. The ozone layer would be depleted, leading to dangerous levels of UV radiation reaching the surface. There would be significant radiation exposure for any life on the surface. This would likely cause a mass extinction event. Not everything would die, but a substantial percentage of species would. The planet might recover eventually, but it would take a very, very long time. From 100 to about 300 light years, we're in what you might call the risky but survivable zone. A supernova at this distance would cause atmospheric damage, increased radiation levels, and potentially significant climate effects. There might be a mass extinction. Current theory suggests that past mass extinctions on Earth might have been triggered by supernovae at roughly this distance. But the planet itself would survive, and life, at least some life, would persist. It would be rough, but not apocalyptic. Beyond 300 light years, you're mostly safe. You'd still see the supernova. It would be bright, perhaps one of the brightest objects in the sky. But the radiation would be diluted enough by distance that it wouldn't cause significant damage. There might be some measurable increase in cosmic ray flux, some atmospheric effects, but nothing that would threaten life on a global scale. So where are we in relation to potential supernova candidates? How safe is Earth, really? Let's take inventory of the neighbourhood. The closest star capable of going supernova is Spica, in the constellation Virgo. It's actually a binary system, 2 stars orbiting each other, and at least one of them is massive enough to eventually explode. Spica is about 250 light-years away. That's, well, it's borderline. It's in that 100 to 300 light-year zone where things could get interesting if it exploded. But here's the good news. Spica is relatively young. It's only about 12 million years old, and stars of its mass live for perhaps 10 to 15 million years. So, we've got a few million years before we need to worry about Spica. That gives us time. Time to develop better technology. Time to potentially leave Earth if we wanted to. Time to at least track Spica's evolution and see it coming. Betelgeuse, which we discussed in the last chapter, is about 650 light-years away. That's well outside the danger zone. When Betelgeuse explodes, whenever that happens, it will be spectacular, but it won't be dangerous. We'll get a light show, not radiation damage. It's the perfect distance, really. Close enough to be brilliant, far enough to be safe. Antares, another red supergiant, is about 550 light-years away. Also safe. Also spectacular when it eventually goes. Rigel, in Orion, is somewhere between 800 and 900 light-years away. Very safe. IK Pegasi, a binary system that might produce a Type Ia supernova, is only about 150 light-years away. But it's a different type of supernova and less dangerous than the core collapse ones we've been discussing. So Earth is actually in a pretty safe neighbourhood, supernova-wise. No massive stars close enough to pose a serious threat. Not now, anyway. Stars move. Our galaxy is rotating. Stars orbit the galactic centre at different speeds. And over millions of years, our neighbours change. In the distant future, we might find ourselves closer to potential supernova candidates. But for now, we're fine. There is, however, an intriguing mystery in Earth's geological record. Scientists have found evidence of past supernova exposure. Specifically, they've found isotopes of iron-60 in ancient rock layers. Iron-60 is not produced on Earth naturally, and it has a half-life of 2.6 million years, which means if we find it, it hasn't been here very long in geological terms. The presence of iron-60 suggests that Earth was exposed to debris from one or more supernovae sometime in the past few million years. The isotope arrived either as dust drifting through the interstellar medium and being captured by Earth's gravity, or possibly from the supernova itself if we pass through its expanding debris cloud. This has led to some interesting speculation. Were these supernovae close enough to affect Earth's climate? Could they have contributed to any of the minor extinctions or climate shifts we see in the fossil record? The evidence is still being debated, but it's a reminder that while we're currently safe, we're not completely isolated from cosmic events. The universe reaches across light years, and sometimes what happens to stars far away has subtle effects even here. Now let's talk about gamma-ray bursts, because these are relevant to any discussion of safe distances from stellar explosions. Gamma-ray bursts are even more energetic than supernovae. They occur when certain types of massive stars collapse, or when neutron stars merge, and they produce focused beams of gamma radiation with energies that make regular supernovae look gentle. If a gamma-ray burst were aimed at Earth from even thousands of light years away, it could cause significant damage. The key word there is aimed. Gamma-ray bursts are directional. They fire their energy out in narrow jets like cosmic searchlights. If you're in the path of one of those jets, you're in trouble. If you're off to the side, you might not even notice it happened. This directionality makes gamma-ray bursts less likely to affect us than you might think. Yes, they're incredibly powerful. Yes, they can affect planets from much greater distances than regular supernovae, but the odds of one being aimed directly at Earth are very low. It's like being worried about laser pointers in a universe full of flashlights. Yes, the laser is more intense, but it has to be pointing exactly at you to matter. There's speculation that a gamma-ray burst might have caused the Ordovician extinction event about 450 million years ago, which wiped out about 85% of marine species. The hypothesis is that a gamma-ray burst from a relatively nearby star stripped away Earth's ozone layer, leading to increased UV radiation and climate disruption. It's an interesting idea, and it's plausible, but we don't have definitive proof. The important thing to remember is that gamma-ray bursts are rare, much rarer than supernovae, and the ones that could affect Earth at significant distances are even rarer. We're talking about events that might happen once every few 100 million years, within dangerous range of Earth, if that. So what's the takeaway from all this distance talk? Earth is, by cosmic standards, remarkably safe. We orbit a stable star that won't explode. We're not particularly close to any stars that will explode. We're in a relatively quiet part of the galaxy, far from the star-forming regions where massive stars are common and supernovae are frequent. This is not an accident, or rather, it might be. One of the prerequisites for complex life is stability. You need time for evolution to work, for complexity to develop, for intelligence to emerge. If Earth were in a region of the galaxy with frequent supernovae, we might not be here to wonder about it. The repeated radiation exposure might have prevented complex life from ever developing. There's a concept in astrobiology called the galactic habitable zone, the idea that only certain parts of a galaxy are suitable for life. Too close to the galactic center, and you're exposed to too much radiation from the supermassive black hole, from frequent supernova, from densely packed stars that might gravitationally disrupt planetary systems, too far from the galactic center, and there might not be enough heavy elements to form rocky planets and complex chemistry. Earth is in what seems to be a sweet spot, not too close to the action, not too far, with enough heavy elements to build a complex world, but not so much radiation that life can't persist, in a region where stars are relatively spread out, where supernovae happen but not too close, where we can observe cosmic violence from a safe distance. It's worth appreciating how fortunate this is. We can study supernovae without being threatened by them. We can learn about stellar death without dying ourselves. We get all the benefits of living in a dynamic, element-rich universe without most of the immediate dangers. There are other parts of the galaxy where this isn't true. Star-forming regions like the Orion Nebula, where massive stars are being born and dying in relatively rapid succession. Those would be dangerous places to have a planet with life. The galactic center with its dense star fields and the supermassive black hole Sagittarius A star, also not ideal for long-term habitation. But here, in our quiet spiral arm, about 26,000 light-years from the galactic center, orbiting a medium-sized middle-aged star, we're safe. And we've been safe for long enough that life had time to develop, to diversify, to become complex, to become intelligent, to become curious about the universe it inhabits. When we look at the night sky and see stars, we're seeing potential futures. Some of those stars will die gently, like our sun will. Others will explode spectacularly as supernovae, will scatter their elements across light years, will leave behind neutron stars or black holes. And we'll see it happen. Not up close, that would be unfortunate, but from our safe distance through our telescopes in our data. Betelgeuse might explode tonight, or tomorrow, or in 10,000 years. We don't know, but when it does, when that light reaches Earth, we'll be here to see it and we'll be safe. We'll be dazzled, amazed, scientifically enriched, but safe. That's the gift of distance. In space, distance isn't just about how far apart things are. It's about having room to exist, to observe, to survive. It's about being far enough from danger to thrive, close enough to beauty to appreciate it. Our safe distance from potential supernova isn't just a convenient astronomical fact. It's one of the reasons we exist at all. It's one of the reasons we can have this conversation, can explore these questions, can imagine the impossible and learn from real observations. The universe is violent. Stars explode, galaxies collide, black holes devour matter, but it's also vast. And in that vastness, there's room for quiet corners, safe harbors, stable regions where life can persist and wonder and grow. We're in one of those corners. And from here, we can watch the universe do its spectacular, violent, creative work, knowing that we're far enough away to be safe, close enough to be amazed. We've taken quite a journey together, haven't we? We've imagined the impossible, our sun exploding as a supernova. We've followed the light, the radiation, the blast wave. We've watched Earth be transformed from a living world into a molten, airless rock. We've explored what gets created in the violence of stellar death. We've looked at real supernovae that humans have witnessed. And we've talked about safe distances, about the cosmic geography that protects us from these magnificent catastrophes. Now it's time to step back and ask, what does all of this teach us? What can we learn from this impossible scenario? Because even though our sun can't explode, even though this entire exploration has been an exercise in imagination, there are real lessons here, real insights about the universe we inhabit, about our place in it, about the delicate balance we exist within. Let's start with the most obvious lesson. We are remarkably fortunate in our cosmic circumstances. Think about all the things that had to go right for us to be here, having this conversation. We needed a star that was stable, not too massive. Those burn too hot and die too young. Not too small. Those might be dim and long-lived, but they have other issues, like frequent stellar flares that could strip away a planet's atmosphere. We needed something medium-sized, something that would burn steadily for billions of years, something that would provide consistent energy without dramatic variations. And we got exactly that. Our sun is a G-type main sequence star, right in the middle of a stellar mass distribution. It's been burning steadily for 4.6 billion years, and it will continue to burn steadily for another 5 billion years. That's a 10 billion year lifetime of stability. That's time enough for planets to form, cool, develop atmospheres. Time enough for life to begin, to evolve, to become complex. Time enough for intelligence to emerge and start asking questions about the universe. If we had orbited a massive star, one destined to go supernova, we'd have had maybe 10 or 20 million years. That's not enough. Life on Earth took over 3 billion years to evolve from single cells to multicellular organisms. Complex life is slow. It needs time. It needs a stable energy source that doesn't change dramatically over geological timescales. We also needed the right location in the galaxy, not too close to regions with frequent supernovae, not so far out that there weren't enough heavy elements to form rocky planets. We needed to be in a place where the violence of stellar death happens, but at safe distances, where we can benefit from the elements created by ancient supernovae without being threatened by nearby ones. And we got that too. Our solar system orbits in a relatively quiet spiral arm of the Milky Way, far from the dense star-forming regions, far from the galactic centre, with its supermassive black hole and high radiation environment. We're in a cosmic suburb, and that's exactly where you want to be if you're trying to evolve complex life. So the first lesson is one of appreciation. We are cosmically lucky, not because the universe was designed for us. It wasn't. But because in a universe vast enough to contain trillions of stars, in a galaxy with hundreds of billions of stars, there are bound to be some places that have the right conditions, and we happen to be in one of them. The second lesson is about the nature of violence and creation in the universe. When we imagine a supernova, our first instinct is to think of it as purely destructive, and on one level, that's true. A supernova destroys the star. It destroys anything nearby. If there were planets around that star with life on them, that life would be extinguished. It's violence on a scale that's hard to even comprehend. But destruction and creation are not opposites in the universe. They're partners. They're two aspects of the same process. Every atom in your body heavier than helium was created inside a star, and most of the heavy ones, the carbon, the oxygen, the nitrogen, the calcium, the iron, were either created in a supernova or scattered by one. You exist because stars died. You are made, quite literally, from the ashes of ancient explosions. The calcium in your bones, the iron in your blood, the oxygen you're breathing right now, all of it was forged in the final moments of massive stars, or in the explosions that ended their lives. There's something profound about that. It means that the most violent events in the universe are also essential to the existence of complex matter. You can't have rocky planets without heavy elements. You can't have life as we know it without carbon, nitrogen, oxygen, phosphorus. And you can't have those elements without stars that lived and died. The universe requires both creation and destruction. Stars must form and stars must die. Worlds must be born and worlds must end. And from that cycle, from that eternal dance of creation and destruction, comes everything interesting. All the complexity, all the beauty, all the life. This isn't just true for the universe at large. It's true for Earth too. Species go extinct, making room for new species. Forests burn, and new growth emerges from the ashes. Even in your own body, cells die and are replaced. A constant process of destruction and renewal that keeps you alive. The supernova is just the cosmic version of this universal principle. It's destruction that enables creation. It's death that makes new life possible. And while we might not want to be too close to one, we can appreciate that they're necessary. They're part of how the universe enriches itself, how it becomes more complex over time. The third lesson is about perspective and scale. We live our lives at human scales. We think in terms of years, decades, maybe centuries, if we're thinking about history. We think in terms of miles, or at most thousands of miles. Our direct experience is limited to one planet, one tiny world, orbiting one average star in one galaxy among trillions. But when we explore questions like, what if the sun exploded? We're forced to expand our perspective. We're thinking about stellar lifetimes measured in millions or billions of years. We're thinking about distances measured in light years. We're thinking about energies so vast. They dwarf anything in human experience. And this shift in perspective is valuable. It reminds us that we're part of something much larger than ourselves. Our individual lives, our civilizations, even our species. We're tiny blips in cosmic time. The sun was here for billions of years before we existed, and it will be here for billions of years after we're gone. That could be depressing, I suppose. You could look at the vastness of space and time and feel insignificant, but I find it oddly comforting. It means that the universe is bigger than our problems, more ancient than our worries, more enduring than our concerns. Whatever happens in our lives, however complicated things get, the sun will rise tomorrow. It will fuse hydrogen into helium, just as it did yesterday, just as it will tomorrow and the day after, and for billions of days to come. There's a stability in that, a reliability. The universe may be violent at extremes, but it's also remarkably predictable. Stars follow rules. Supernovae happen according to physics we understand. The cosmic cycles turn, and we can trust them to keep turning. The fourth lesson is about knowledge and understanding. 1,000 years ago, when Chinese astronomers saw the guest star of 1054, they had no idea what they were witnessing. They knew a new star had appeared, but they couldn't have known it was a supernova, that it was a star exploding 6,500 light-years away, that it was creating heavy elements and scattering them across space. Today, we know. We understand the physics of stellar collapse. We can explain why massive stars explode and why our sun won't. We can predict which stars are supernova candidates and which aren't. We can measure the distances, calculate the energies, understand the processes. This knowledge doesn't make supernovae less wondrous. If anything, understanding them makes them more amazing. The fact that we can comprehend such extreme physics, that we can unravel the complex chain of events from core collapse to neutron star formation to element creation, that's remarkable. And this knowledge makes us safer, because we know which stars are dangerous and which aren't. We know that we're safe. We don't have to wonder if the sun might explode tomorrow. We know it won't. Not because of faith or hope, but because we understand how stars work. This is one of the great gifts of science. It replaces fear with understanding. Ancient peoples might have feared eclipses as omens of disaster. We understand them as natural, predictable alignments of celestial bodies. Ancient observers might have feared that a bright new star was a portent of doom. We understand it as a supernova, a natural process in stellar evolution. The universe is less scary when you understand it. More beautiful, certainly. More complex, definitely. But less scary. The fifth lesson is about gratitude for gentleness. We've spent hours imagining violence. The explosion of the sun, the destruction of Earth, the unsurvivability of it all. And through that exploration, we've come to appreciate something we usually take for granted. The sun is gentle. Every morning the sun rises, not too hot, not too cold, providing exactly the amount of energy Earth needs to maintain liquid water, to support life, to make our world habitable. It's been doing this for billions of years. It will keep doing this for billions more. That's not dramatic, There's no explosion, no violence, no sudden transformation. Just steady, reliable, consistent energy output. The sun goes to work every day, fuses hydrogen into helium, radiates energy into space, and supports an entire biosphere on the planet we call home. We don't usually think about how remarkable that steadiness is. We expect the sun to rise. We expect it to provide warmth and light. We expect it to be there, unchanging, reliable, and it meets those expectations every single day. But imagine living with a variable star. Some stars change their brightness dramatically over short periods. They flare up, dim down, create an unstable environment for any planets around them, or imagine living around a massive star, knowing that in a few million years, a geological eye blink, your star will explode. We don't have to imagine that. We have a gentle star, a stable star, a star that does its job without drama, without variation, without any tendency toward violence. And that gentleness is a gift. It's the gift of time, of stability, of a safe environment in which life can flourish. The sixth lesson, and perhaps the most important one, is about impermanence and change. Everything we've discussed, the explosion of stars, the creation of elements, the cycling of matter through the universe, it's all about change. Nothing in the universe is permanent. Stars are born, live, and die. Planets form and are eventually destroyed. Even black holes, those seemingly eternal objects, will eventually evaporate through Hawking radiation, though that takes an incomprehensibly long time. Change is not just inevitable, it's essential. Without stars dying and scattering their elements, we wouldn't have the raw materials for new stars and planets. Without change, the universe would still be just hydrogen and helium, simple and unchanging and ultimately boring. This applies to us too. We're temporary. Our civilization is temporary. Our species is temporary. Even our planet is temporary, though its timescale is so long that it's effectively eternal from our perspective. But in the grand cosmic scheme, Earth will eventually be consumed when the sun becomes a red giant. That's billions of years away, but it will happen. And that's okay. That's how the universe works. Everything that exists is temporary, but from that impermanence comes the possibility of newness, of change, of transformation. The atoms in your body have been many things before they were you. They've been stars and clouds of gas and rocks and ancient organisms, and after you they'll be something else. They'll continue cycling through the universe, taking new forms, becoming parts of new things. There's something almost comforting about that continuity. You're not separate from the universe. You're part of it. You're a temporary arrangement of atoms that have existed for billions of years and will exist for billions more. You're a way for the universe to experience itself, to think about itself, to wonder about itself. And when we explore questions like, what if the sun exploded? We're exercising that capacity for wonder. We're using the intelligence that emerged from billions of years of stellar evolution and biological evolution to understand the very processes that made us possible. The final lesson is the simplest one. We're home. This planet orbiting this star in this galaxy, in this universe, this is where we are. This is where life emerged, where it evolved, where it became us. And this place, for all its ordinariness on a cosmic scale, is extraordinary to us. Earth is the only planet we know of with life, the only one. We've studied dozens of planets and moons in our solar system, and we've detected thousands of planets around other stars. And so far, we haven't found life anywhere else. Maybe it's out there. The universe is vast, and it would be strange if life only happened once. But we haven't found it yet. So Earth is special, not because it's at the center of the universe or because it was specially created for us. It's special because it's ours, because it's where we are, because it's the only home we've ever known, and that home exists under the light of a gentle sun, safe from cosmic violence, blessed with stability and time. When we imagine that sun exploding, when we walk through the catastrophe that would result, we're reminded of how much we depend on that stability, how fortunate we are to have it. So what does all this teach us? It teaches us to appreciate what we have, to understand the cosmic processes that made us possible, to recognize our place in the universe, not at the center, but as part of the whole, temporary but meaningful, small but significant. It teaches us that violence and creation are intertwined, that change is essential, that impermanence is not something to fear, but something to accept as the nature of existence. And it teaches us that our sun, that ordinary yellow dwarf star, is exactly what we need. Not too massive, not too small, not variable, not dying, just steady, gentle, and reliable. Tomorrow, the sun will rise, just as it did today, just as it has for billions of days before, and we'll be here to see it, to feel its warmth, to live under its light. And that really is everything. We've explored the physics of supernovae, the violence and creation, the real observations and the safe distances. But supernovae aren't just scientific phenomena, they're also cultural events. Throughout human history, when people looked up and saw a new star in the sky, they didn't just observe it, they interpreted it. They gave it meaning. They wove it into their understanding of the cosmos and their place in it. Let's explore how humanity has understood and responded to supernova throughout history, and how these cosmic explosions have influenced our culture, our mythology, and our sense of ourselves. The earliest recorded supernovae that we know about come from ancient Chinese astronomical records. Chinese astronomers were remarkably systematic in their observations. They kept detailed logs of celestial events, comets, planets, meteors, and most importantly for our purposes, guest stars. These were stars that appeared when no star had been visible before, remained visible for weeks or months, and then faded away. The Chinese approach to these guest stars was practical and observational. They recorded when they appeared, where in the sky they were located, how bright they were, and how long they remained visible. These weren't just casual observations, they were official records kept by court astronomers whose job was to track the heavens and report anything unusual. But these observations weren't purely scientific, at least not in the modern sense. In ancient Chinese cosmology, events in the heavens were connected to events on Earth. The emperor's mandate to rule came from heaven, and celestial phenomena could be interpreted as signs of heaven's approval or displeasure. A guest star might be seen as an omen, good or bad, depending on various factors like where it appeared, when it appeared, and what else was happening in the empire at the time. The supernova of 185 CE, for instance, was recorded in the Book of Later Han. The astronomers noted its position, its brightness, and its duration, but they also would have been thinking about what it meant for the empire. Was it a good sign? A warning? What did heaven want the emperor to know? We can appreciate this dual nature of their observations. They were doing real astronomy, recording data that modern scientists can still use to study these ancient supernovae. But they were also doing something deeply human, trying to find meaning in what they saw, trying to understand their place in a cosmos that seemed to be speaking to them through the appearance of new stars. Other cultures had their own interpretations of sudden celestial appearances. In medieval Europe, when Tycho Brahe observed his supernova in 1572, he was challenging the prevailing Aristotelian view that the heavens were perfect and unchanging. The appearance of a new star was philosophically troubling, because it suggested that the celestial realm was subject to change, just like the earthly realm. This might seem like a small thing now, but it was part of a larger shift in thinking that we call the scientific revolution. The idea that the heavens could change, that new things could appear and old things could disappear, helped break down the rigid distinction between the earthly and the celestial. It helped pave the way for the modern understanding of the universe as a dynamic place where things happen, rather than a perfect, eternal, unchanging realm. Kepler's supernova in 1604 had similar philosophical implications. Both Tycho and Kepler were careful observers who documented these events systematically, but they were also working in a time when the line between astronomy and astrology was blurry, when studying the stars meant thinking about their influence on human affairs. It's interesting to consider what it must have been like to see these supernovae without understanding what they were. Imagine looking up and seeing a star so bright it's visible during the day. It's not the sun. You can see both the sun and this new star simultaneously. It doesn't move like a planet or a comet. It just sits there in the sky, brilliant and impossible, night after night, slowly fading over weeks or months. You'd naturally think it meant something. You'd try to interpret it. Was it a message from the gods? A sign of coming war or peace, famine or plenty? Was it related to the birth of someone important or the death of a ruler? Without the framework of modern astrophysics, without understanding stellar evolution and nuclear fusion, you'd have to find some other way to make sense of this extraordinary event. And in a way, those ancient observers were right to think supernovae meant something, just not in the way they imagined. Supernovae do have meaning. They're part of how the universe creates the elements necessary for life. They're part of the cycle of stellar birth and death that enriches the cosmos over time. But that meaning is physical, not mystical. It's about chemistry and physics, not omens and portents. The transition from seeing supernovae as omens to understanding them as physics is one of the great achievements of human thought. And yet, we haven't entirely lost that sense of wonder, that feeling that these events are special, that they mean something. We just understand the meaning differently now. When Carl Sagan said, "We are star stuff," he was making a scientific observation. We're literally made of atoms that were created in stars. But he said it in a way that resonated culturally, that gave people a sense of connection to the cosmos. It's scientific fact, but it's also poetry. It gives meaning to supernovae without requiring them to be omens or messages. They're meaningful because they're part of the process that made us. This phrase, "we are star stuff," has become part of modern culture. You see it on t-shirts, in songs, in tattoos. People find comfort and wonder in the idea that they're connected to the cosmos at such a fundamental level. It's a modern mythology, based on physics rather than ancient beliefs, but it serves some of the same psychological needs. It helps us feel connected to something larger than ourselves. In literature and art, supernovae have become symbols of transformation, of endings that are also beginnings, of destruction that enables creation. The phoenix rising from the ashes is an ancient image, but it maps beautifully onto what we now know about supernovae, death that scatters the seeds of new life across the cosmos. Science fiction writers have used supernovae as plot devices, as catastrophes that force civilizations to flee their homeworlds, as sources of exotic materials or energies. Arthur C. Clarke wrote stories involving stars going supernova. Larry Niven explored what it would be like to see a distant supernova and know it would reach you eventually. These stories take the physics and extrapolate, imagine scenarios, explore consequences. But beyond the obvious dramatic potential of exploding stars, supernovae appear in more subtle ways in culture. They've influenced how we think about impermanence, about the cycles of the universe, about our place in cosmic time. The knowledge that even stars die, that nothing is permanent, that even the seemingly eternal is temporary, shapes how we think about existence itself. There's a philosophical tradition, particularly in certain schools of Buddhism, that emphasizes impermanence as a fundamental truth of existence. Everything that arises will pass away. Nothing is permanent. And there's something almost comforting in applying this, not just to human lives or civilizations, but to stars, galaxies, even the universe itself. We're all temporary together. Humans and planets and stars and galaxies. We're all part of the same cosmic flow of arising and passing away. Modern astronomy has given us a timescale for this impermanence that ancient philosophers couldn't have imagined. Stars live for millions or billions of years. The universe itself is nearly 14 billion years old. These are timescales so vast, they're almost meaningless to human intuition. But they're still finite. Even on cosmic scales, things change. Stars are born and die. Galaxies evolve. The universe expands and will continue to expand, perhaps forever. This knowledge has filtered into how we think about ourselves. We live in a culture that's much more aware of cosmic scales than any previous human culture. We know we're on a planet orbiting a star in a galaxy, among billions of galaxies. We know about the Big Bang, about stellar evolution, about the eventual heat-death of the universe billions of years from now. Does this make us feel small and insignificant? Sometimes, perhaps, but it can also make us feel connected, part of something vast and ancient and ongoing. We're not separate from the universe. We're made of it, shaped by it, part of its evolution. When we observe a supernova, whether it's SN 1987A, or waiting for Betelgeuse, or studying the Crab Nebula, we're not just doing science. We're also engaging in a kind of cultural practice, a modern form of looking at the sky and finding meaning. The meaning is different than what ancient Chinese astronomers found, but it's no less profound. We're seeing the universe change. We're witnessing stellar death. We're observing the processes that created the elements we're made of. We're connecting ourselves to cosmic history, to the life cycles of stars, to the grand sweep of how the universe enriches itself over time. In education, supernovae have become one of the most effective ways to teach people about their cosmic origins. The story goes something like this. The universe began with a Big Bang, but that only created hydrogen and helium stars formed from this simple material and began fusing it into heavier elements. Massive stars created the heaviest elements and scattered them through supernovae. Those elements formed new stars and planets, eventually on at least one planet around one star in one galaxy. Those elements formed life, and that life evolved into us. It's a powerful narrative. It's scientifically accurate, but it's also a creation story, a way of understanding where we came from and how we got here. It's replaced older creation stories for many people, not because it's more emotionally satisfying, it probably isn't, but because it has the virtue of being true, of being based on observations and physics rather than mythology. And yet, there's something mythological about it too, in the best sense. It's a grand story about origins, about the transformation of simple matter into complex structures, about how the universe gave birth to beings capable of understanding their own origins. In popular culture, the concept of supernovae has become widely known, even if the details are often fuzzy. People know that stars can explode. They know it's powerful and dramatic. They might not understand the physics of core collapse or the difference between type Ia and type 2 supernovae, but they grasp the basic concept. And that's actually remarkable. It's a piece of advanced astrophysics that's become common knowledge. This widespread awareness changes how we think about the universe. Previous generations thought of stars as eternal lights in the sky. We know they're temporary, that they have life cycles, that they're born and die like everything else. This knowledge shapes our cosmic perspective in subtle ways. There's also something beautiful about how supernovae have become a bridge between different cultures and time periods. When we study the Crab Nebula, we're studying the same object that Chinese and Japanese astronomers saw in 1054. We're connecting across nearly 1,000 years of time, looking at the same cosmic event through different lenses. They saw a guest star, we see a supernova remnant, but it's the same thing. And when Betelgeuse eventually explodes, whenever that is, people all over the world will see it. It won't be interpreted as an omen or a message from the gods. It will be understood as physics, as a star ending its life in a spectacular way. But people will still look up in wonder. Children will point at the bright new star. Artists will be inspired by it. It will be talked about, written about, photographed, studied. That sense of wonder, that response to something extraordinary in the sky, that's the same across cultures and time periods. The interpretation changes, the understanding deepens, but the fundamental human response to cosmic phenomena remains. We look up, we notice, we wonder, we try to understand. Supernovae have also influenced how we think about endings and transformations more generally. The idea that death can be creative, that destruction can lead to new creation, that something can end and yet leave something beautiful behind. These aren't just scientific facts about stellar evolution, they're ideas that resonate with human experience. We see our own lives reflected in the cosmic cycle. Things end, but other things begin. We lose people, but we remember them, and their influence continues. Projects finish, relationships change, stages of life conclude, and yet life continues, transformed but not diminished. The supernova becomes a metaphor for transformation through destruction, for the necessary ending of one thing to make space for something new. It's not a perfect metaphor. Real supernovae are far more violent than anything in human experience, but it's a powerful one. In music, there are songs about supernovae, about stars exploding, about cosmic themes. The band Oasis had a song called Champagne Supernova, which doesn't make a lot of literal sense, but captures something about brightness and transformation. Other artists have used stellar imagery to talk about human experiences, burning bright, fading away, leaving light behind. In visual art, images of supernovae and supernova remnants have become iconic. The Hubble Space Telescope has captured stunning images of nebulae, of the Crab Nebula with its intricate filaments, of other supernova remnants glowing in various colours. These images are scientifically valuable, but they're also simply beautiful. They appear in galleries, in books, as desktop backgrounds. They've become part of our visual culture, our shared sense of what the universe looks like. And perhaps most significantly, knowledge of supernovae has influenced how we think about our place in the universe and our relationship with the cosmos. We're not separate from it. We're not observers standing outside looking in. We're part of it, made from it, shaped by billions of years of cosmic evolution, including the explosions of countless ancient stars. This isn't just an abstract scientific fact. It's a framework for understanding ourselves, our origins, our connection to the universe. It's a modern cosmology, a way of making sense of existence based on physics and observation rather than mythology and revelation. When we look at supernovae through this lens, not just as physics but as cultural phenomena, as things that have shaped human thought and continue to shape how we understand ourselves, they become even more fascinating. They're not just exploding stars, they're part of human story, part of how we've tried to understand the cosmos, part of how we connect ourselves to something larger. Tomorrow, the sun will rise, just as it always has, and somewhere in the universe a star will explode. And perhaps millions of years from now, observers on a planet we can't even imagine will look up at their sky and see a new light, and they'll wonder what it means, just as we have, just as humans always have. We're near the end of our journey now. We've imagined the impossible, explored the physics of stellar death, learned about real supernovae, and discovered how these cosmic events have shaped human culture and understanding. And now, having walked through all of that, having seen what could happen if our sun were the kind of star that explodes, we can return to where we started, to our sun, our actual sun, and appreciate it for what it really is. A gift, a gentle, steady, wonderfully boring gift. Let's talk about what we actually have. Not the imaginary massive star that explodes, not the dramatic death we've been exploring, but the real sun, the G-type main sequence star that's been faithfully doing its job for 4.6 billion years and will continue for another 5 billion. The sun is, in many ways, remarkably average. It's not the biggest star. There are stars hundreds of times larger. It's not the smallest. There are red dwarfs much smaller and dimmer. It's not the hottest, not the coolest, not the brightest, not the dimmest. It sits right in the middle of almost every stellar category you can think of. And that averageness is perfect, because average in the cosmic sense means stable. It means predictable. It means the kind of environment where life can develop over billions of years without being disrupted by dramatic stellar variations. Consider what the sun does day after day, year after year, millennium after millennium. Deep in its core, about 600 million tons of hydrogen are fusing into helium every second. This releases an enormous amount of energy, enough to power all of human civilization millions of times over. That energy works its way from the core through the radiative zone, through the convective zone, and finally radiates into space as light and heat. And it does this at a remarkably steady rate. The sun's output varies. Yes, there are small fluctuations related to sunspot cycles, brief flares, minor variations, but these are tiny compared to what some stars do. Some stars vary their output by factors of 2 or more. Some have flares so powerful they could strip away a planet's atmosphere. Some pulse, some fluctuate wildly. Some are in binary systems where they exchange mass in dramatic bursts. Our sun just shines, steadily, reliably, with variations so small that life on Earth barely notices them. That's the gift. Not drama, not excitement, but steadiness, predictability. The kind of stable environment where complex systems can develop. Think about what that stability has enabled. For the first billion years or so of Earth's history, life was simple. Single-celled organisms, bacteria, archaea-basic, but alive. And they could exist because the sun provided steady energy. Not too much, not too little. Just enough to keep Earth in the habitable zone, that narrow range of distances from a star where liquid water can exist on a planet's surface. Over the next few billion years, life became more complex. Multicellular organisms evolved. Plants developed photosynthesis, directly harnessing sunlight to create food. Animals evolved to eat the plants or to eat other animals that ate the plants. Entire ecosystems developed, all ultimately powered by that steady stream of sunlight. And through all of this, through billions of years of evolution, through ice ages and warm periods, through mass extinctions and recoveries, the sun kept shining. Not perfectly constant, but stable enough that life could adapt to its minor variations rather than being wiped out by dramatic changes. When we compare our sun to the massive stars that do explode, the contrast is striking. Those massive stars are spectacular. They're bright, they're energetic, they're dramatic, but they're also short-lived. A star 20 times the mass of our Sun might only live for 10 million years. That's not enough time for complex life to evolve. You might get single-celled organisms if you're lucky, but you're not getting forests and oceans full of diverse life, and certainly not intelligent species wondering about their place in the universe. Our Sun's gift is time. 5 billion years of past stability. 5 billion more years of future stability. 10 billion years total, enough for life to originate, diversify, become complex, become intelligent, develop technology, and potentially spread beyond its home planet. That's the gift that only a medium-mass, medium-lifetime star can give. Let's think about the Sun's death too, because even that is a gift of sorts. When the Sun eventually does die, it will do so gradually. Over the course of the next billion years or so, it will slowly get brighter as it ages. This will eventually make Earth uninhabitable. The oceans will evaporate. The temperature will rise beyond what life can tolerate. But this happens so slowly that if humanity survives, we'll have plenty of warning, plenty of time to adapt, to leave, to find other worlds. In about 5 billion years, the Sun will exhaust the hydrogen in its core and begin to expand into a red giant. This process takes millions of years. Again, plenty of warning if anyone's around to notice. The Sun will swell until it possibly engulfs Mercury and Venus, maybe even Earth. But this isn't a sudden explosion. It's a gradual transformation, predictable and slow. After the red giant phase, the Sun will shed its outer layers in a planetary nebula, a beautiful expanding shell of gas, and what's left will be a white dwarf, a dense remnant about the size of Earth, slowly cooling over trillions of years. It's a peaceful death, as stellar deaths go. Dignified, gradual, the kind of death that gives any observers plenty of time to prepare, to say goodbye, to move on to other stars. This is in stark contrast to the supernova we've been imagining, that death gives you 8 minutes of warning if you're very lucky. This death gives you millions of years of warning. That's a meaningful difference if you're trying to plan for the long-term survival of your species. The Sun's gentleness extends to other ways too. It doesn't have a companion star that it's exchanging mass with in violent bursts. It's not part of a close binary system where gravitational interactions could destabilize planetary orbits. It's a single star with a well-behaved planetary system that's been stable for billions of years. The Sun's magnetic field, while complex and occasionally active, isn't strong enough to be disruptive to life on Earth. Yes, we get solar flares and coronal mass ejections, and these can affect satellites and power grids, but they're not strong enough to strip away our atmosphere, to sterilize the surface, to make the planet uninhabitable. They're more like cosmic weather, occasionally inconvenient, but not existential threats. Even the Sun's location in the galaxy is gentle. We're far from the chaotic galactic center, far from regions of active star formation where supernovae are common. We're in a relatively quiet spiral arm, moving through space at a pace that keeps us safe from hazards, while allowing us to enjoy a stable environment. All of these factors together, the Sun's mass, its age, its stability, its location, its solitary nature, they all contribute to creating the kind of environment where life can not just exist but flourish, where evolution can work over billions of years without being repeatedly interrupted by catastrophes, where intelligence can develop and civilization can emerge and technology can advance. When we look at the Sun, we usually see it as background. It's just there, doing what it's always done, not demanding attention, and maybe that's appropriate. The best gifts are often the ones we don't have to think about, the ones that just work reliably, that support us without drama or fanfare. But having imagined what would happen if the sun were different, if it were massive enough to explode, if it were variable and unpredictable, if it were in a chaotic binary system, we can appreciate what we have. We can see the sun, not as background, but as the foundation of everything we are, everything we've ever been, everything we might become. Every breath you take is powered by the sun. The oxygen was created by plants using sunlight. The food you eat was grown using energy from sunlight, either directly through photosynthesis or indirectly through the food chain. The warmth you feel on your skin on a sunny day is light that left the sun's surface 8 minutes earlier and travelled 93 million miles to reach you. The weather patterns that bring rain to water crops, those are driven by the sun's heat. The ocean currents that moderate Earth's climate, powered by the sun. The seasons that give variety to our years, caused by Earth's tilt relative to the sun. The day-night cycle that structures our lives, caused by Earth's rotation relative to the sun. Everything we have, everything we are, traces back to this one star. And that star is gentle, stable, patient. It gives without asking anything in return. It shines on everyone and everything equally, on forests and deserts, on oceans and mountains, on cities and wilderness, on all of humanity regardless of nation or belief or circumstance. There's something almost philosophical about that universality. The sun doesn't play favourites. It doesn't withhold its light from some and grant it to others. It just shines, and anyone on the day side of Earth can benefit from its light and warmth. It's a cosmic commons, a shared resource that belongs to everyone and no one. When ancient peoples worshipped the sun, they weren't being primitive or misguided. They were recognizing something fundamentally true, that the sun is essential to life, that without it we would have nothing, that its presence is worthy of reverence. We don't worship the sun now, not in a religious sense, but we can still revere it. We can still recognize its importance, still feel gratitude for its presence. And we can recognize that having this particular sun, this gentle medium mass main sequence star, is not something we earned or deserved. It's luck, cosmic chance. In a universe with trillions of stars, in a galaxy with hundreds of billions of stars, we happen to orbit one that's exactly what we need, not too massive, not too small, not variable, not unstable, not in a dangerous location, not in a binary system. Just perfect for supporting life. That's worth appreciating, worth being grateful for. Not in a religious sense necessarily, but in a simple recognition of how fortunate we are. We could have orbited a different star. We could have been in a different part of the galaxy. We could have faced cosmic hazards that made complex life impossible, but we didn't. We got the gentle sun, the stable environment, the billions of years of steady light and warmth. And because of that, we're here. Breathing air created by photosynthesis, eating food grown in sunlight, living on a world that's maintained at just the right temperature for liquid water and complex life, thinking about the universe, wondering about our place in it, imagining what would happen if things were different. The sun has given us the gift of existence, and with it the gift of curiosity, of wonder, of the ability to look at the stars and ask questions, including the question we've been exploring tonight. What if the sun exploded? The answer, as we've seen, is catastrophic, but the fact that we can ask the question, can explore its implications, can understand the physics involved, that's a gift too. A gift that only comes from having a stable star that gave life enough time and stability to evolve intelligence. Tomorrow morning the sun will rise, just as it did this morning, just as it has every morning for billions of years, and it will shine steadily through the day, providing light and warmth, powering photosynthesis and weather patterns, and all the invisible processes that keep Earth habitable. It will do this without fanfare, without asking for recognition or gratitude, without any awareness that we're here, watching it, depending on it, appreciating it. But we are here, and we do appreciate it, and having imagined a universe where our sun could explode, where we lived under a different kind of star, we can return to reality with deeper appreciation for what we actually have. A gentle sun, a stable sun, a gift of a sun, the perfect star for the only home we've ever known. And so we find ourselves at the end of this impossible journey. We've imagined violence, explored catastrophe, walked through the physics of stellar death. We've seen what could happen if our sun were different, if it were massive enough to explode, if we lived under a star with a dramatic rather than gentle end written into its future. But here's the wonderful truth we return to. Our sun is still there, still shining, still doing exactly what it's been doing for 4.5 billion years, still fusing hydrogen into helium, still radiating light and warmth, still being perfectly, wonderfully, reliably boring. Tomorrow it will rise again, and the day after that, and for billions of days to come. That's not just a fact, that's a promise written in the physics of stellar evolution. Our sun cannot explode. It will die eventually. Yes, everything dies, but it will die slowly, peacefully, over millions of years, giving any future observers plenty of time to adapt, to leave, to find new homes under other gentle stars. We explored the impossible to appreciate what's real. We imagined destruction to understand how fortunate we are to have stability. And now, having made that journey together, we can return to our ordinary lives under our ordinary star, with maybe just a little more appreciation for how extraordinary that ordinariness really is. If you've enjoyed this exploration of cosmic violence and stellar physics, if you found something worthwhile in these late-night wanderings through the impossible, I'd be grateful if you'd subscribe to the Sleepy Astronomer. There are more cosmic questions to explore, more impossible scenarios to imagine, more ways to appreciate the universe we actually inhabit. And if this particular journey resonated with you, a like helps others discover these quiet explorations of space and time. Thank you for traveling with me tonight, for imagining the impossible, for wondering, for questioning, for being curious about how the universe works. The sun is still there. You're still here. And that, when you think about it, is a kind of cosmic miracle, not because it's unlikely, but because it's exactly right, exactly what needed to happen for you to be here, listening, wondering, alive under the light of a gentle star. Sleep well, safe under your stable sun. Dream of exploding stars if you like. They're beautiful in their violence, essential in their creativity. But when you wake, the sun will be there, gentle and reliable, just as it's always been. Good night from the Sleepy Astronomer. May your dreams be full of stars, and may you wake to the light of one that will never surprise you with violence, only with its faithful, steady presence. Until we meet again under the same sky.